This is the journey that we have all had until now. So until now, we have all studied about uh, the different CNN, convolutional neural networks is what we have studied. We've studied about the different architectures, and we've also studied about transfer learning. And transfer learning is basically the overall philosophy where you don't have to build something from scratch. So if you're trying to solve a particular problem, then you will not have to kind of build something entirely from scratch. You can kind of already use a pre-trained model which has been trained on a different data set, and you can just retrain that model or realign that model with respect to your specific task. So that is one of the ways how transfer learning can be implemented. So if you want to go back and if you already have a pre-trained model that has been trained on a particular task, then you don't have to build a fresh model to learn something new. You can pretty much use the same pre-trained model on and incrementally plug that into that new task, and you can still learn. And that's another very interesting idea that we've talked about so far. So once again, so far, our problems, whatever we have studied right till now, as Mr. Jagdish also shared, has been primarily on classification. Right. So you're given a particular picture and you're trying to predict what is the object in the picture. You're just trying to, let's say you look at a cat right now, and one of the things that you've done is you're looking at the example of the cat and you're trying to, and you're passing it through a convolutional neural network. And all that you're trying to do is you're trying to predict what class that particular object belongs to. Is it a cat? Is it a dog? Is it a bird? Is it an elephant? And that is pretty much what you have done. And the general idea of computer vision, what we have studied until now, has been that. So what is a convolutional neural network at a high level? What is a CNN? What do you mean by a convolutional neural network? A convolutional neural network is nothing but it's a feature extraction layer. So what we are going to do here? How do we work with this thing? So what we'll do here is we'll take that entire picture of the cat and we'll pass it through multiple convolution ReLU max pooling, convolution ReLU max pooling. We pass it through multiple convolution layers, and right at the very end, after passing it through many convolution layers, right at the very end, we end up getting the features of the picture. I repeat again, you start off with a particular image of the cat or image of anything for that matter, and once you pass it through many convolution layers, convolution layer 1, convolution layer 2, convolution layer 3. So once you take a particular picture and once you pass it through many convolution layers, right at the very end, you end up getting features of the image. So in this case, when you take that picture of the cat and when you pass it through multiple convolution layers, what you end up getting are features of the cat. Okay, I repeat, what you end up getting are features of the cat. And then what we are trying to do is we are trying to use those, we are trying to use those cat features. We are trying to use the features of the cat. And based on that, we are trying to do a prediction. We are trying to basically find out what is the probability that is a cat, what is the probability it's a dog, and so on and so forth. That's the crux of what we have learned so far in terms of classification. Right. So the convolution layers are primarily acting as feature extractors. And once you extract the features of the cat, the next layer will be a dense layer. You pass it through, let's say, dense of 5, which will tell you the 5 different class probabilities. That is pretty much what we have studied until now in terms of classification. Right. Now, what we are trying to do differently with respect to object detection and object localization is we are trying to also figure out the where part. This is exactly where this particular module comes in handy. So here we are actually trying to figure out the where part. Not only are we trying to figure out what is the object in the picture, but we're actually trying to figure out where is the object in the picture. There are lots of applications of the where. If you specifically focus on that particular where keyword, there are lots of applications where this particular where keyword gets used, the where problem statement gets used. A very common use case could be face detection or facial recognition kind of use cases. I think if you look at your modern smartphones, let's say you're trying to take a selfie using one of your modern smartphones, and if you point your selfie, if you point your camera to your face, it will automatically put a bounding box around your face. Right? If you put your camera near your face, it will automatically put a bounding box near your face, and it will say that, hey, I think I see a face here, and I think I see a face here. You try a group photo. You try to point your camera at a group of people, and once again, wherever it sees faces, it will basically put bounding boxes around those faces. Okay, I repeat, wherever it sees faces, it will effectively kind of put bounding boxes around those faces. That is the crux of what object detection is basically about. And not only will it do object detection, it will do a range of other things. It will not only explicitly do object detection, but it will also do a range of other things. In this case, it will go back and do face recognition. It will not only put a box around that person, but it will also go back and find out the person's age, the person's emotion, the person's name, a whole lot of other activities it can go back and. Okay, but the most important thing is we are trying to figure out the where. Okay, another great use case of this could be surveillance cameras, security and surveillance use cases in airports, or even traffic surveillance, city surveillance, the general city security safety kind of use cases we have. Number plate detection. If a particular vehicle on the road is making a kind of a violation, a road violation, then automatically we can kind of scan that particular vehicle, put a bounding box around that particular vehicle, and extract the number plate of the vehicle, and we can go back and try to read the number plate and automatically send fines to the person to whom the car basically belongs. So this is another wonderful use case where we can kind of use computer vision models to specifically object detection models to go back and not only kind of identify what object it is and where the object is, but once we are able to find that car, let's say there's a car right down at the corner which is jumping a red light. There's a traffic signal here, and let's say this particular car jumped a red light. So the models will automatically put a box around that particular car. The models will automatically put a kind of a box around that particular car, and what will happen is what will happen is it will automatically go all the way down to the number plate of the car and try to read what the number plate of the car is. So that is one more object detection model that will work out, right? There are lots of use cases, and I'll be getting into those pieces as we go along. And specifically, the entire computer vision piece is broken down. I think this is the entire advanced computer vision module. I just wanted to lay out the context so that people are comfortable. So this is primarily the agenda for today: object localization and object detection. And I know, we are calling it only object detection, but actually, you cannot understand object detection without knowing object localization. So they are both topics that go hand in hand. So the primary topic, I know we call it object detection, but basically these are the two terms that we kind of use. And just to right at the outset, just to clarify, because I understand people should know these things right up front before we even jump into anything. And just to lay down the different types of computer vision problems, basically, which will also be very, very important and very good to actually know, very good to actually understand right up front, right at the outset. So what are the different types of computer vision problems we even have? Let's see that. Let's understand that. So just a minute. I am just trying to open it up from my Google Images actually. This is a nice picture, but actually I'm not able to kind of zoom it and open it properly. So I think this will do. This will do. You're able to see this. Yeah, this is a very beautiful depiction of the entire landscape of what we are trying to study in advanced computer vision this weekend and next weekend, also 25th. I think we have another session. This is the whole landscape of what we are trying to. So this is what you have done so far, where I show you a particular object in the picture and you try to classify what object it is. It's a cat in the picture. So one part of what you're doing is you're looking at a particular object and you're trying to classify what is that object. This is the part that you've already done with respect to CNNs, transfer learning, and a whole lot of other stuff. What we are doing today is basically localization and detection. This is the part where you're, in addition to identifying what is the object, you are also trying to identify where is the object. And so now in localization, what you're doing is you are not only identifying what is the object in the picture, but you're also trying to identify where is the object in the picture. You're trying to put a bounding box around that particular object. So given a particular image, you are trying to identify where is the object in the picture and what is the object corresponding to that picture. So there are two things that you're trying to. I repeat, given a particular image, you're trying to identify where is the object in the picture and what is the object in the picture. What is the object corresponding to that picture? So where is the object in the picture? We can see the bounding box that is coming around the cat. So we can see where the bounding box is coming around the cat. So where is that object in the picture? So we can see that. And the second thing we are doing is we can say what is the object in the picture. Okay. So to answer the where part, we can see the bounding boxes are basically coming. So we are just putting bounding boxes around the cat to identify this is where the cat is. And we are also saying, okay, this is the cat. So just remember, localization is mostly about dealing with a single object. Now, once we extend this for multiple objects, we call it detection. That is the only difference between localization and detection. Localization is with respect to a single object. When we have a single object, we form a single bounding box around that object. Whereas detection is more real world, where we kind of real world problems are all dealing with multiple objects, where we are trying to identify where are the objects and what are the objects. So where are the objects? There is an object here, there's an object here, there's an object here, there's an object here. So identify where are the objects, and then identify what are the objects, what are the classes of the objects. That is what we are trying to do specifically with respect to the detection problem. And finally, we have something called the segmentation problem. So one thing that you will observe in object detection is it's actually kind of it's kind of little inaccurate. Although it works pretty well, it works in many real world applications. Starting with Facebook, I think Facebook started implementing this right all the way back in 2009, 10, when even before that, when it started implementing those photo tagging models. All of you recall, like you hover over a person's photo, and Facebook automatically puts a box around that person's face. Wherever the faces are there, Facebook will automatically put bounding boxes, and it will actually even tell you who that person actually is. When you try to tag, Facebook will automatically recommend that, hey, is this person? Is it this person? So the nearest match will typically come up right in the beginning. So it is actually implementing object detection there. It's looking at that entire picture, and it's trying to kind of identify where are the faces and what are the persons corresponding to those faces. Who are the persons corresponding to those respective faces? Okay, so this is pretty much what we have seen. But the problem with object detection is that it's very inaccurate. The models, if you honestly see, the models are actually pretty inaccurate. Object detection models are pretty inaccurate because the bounding box that you end up drawing, whatever bounding box that you end up drawing, that bounding box is actually, not covering the entire thing, right? It's one way to look at it. So whatever bounding box that you have drawn here, this is the bounding box corresponding to the dog, the duck, the cat, This bounding box that you have drawn right now, this bounding box does not completely cover that object, but there are some gaps that we are able to see. Now this is not a great, now this is absolutely fine for normal use cases, like let's say identifying some baggages, surveillance security use cases, or photo tagging, or the camera applications we talked about, vehicle detection on roads. It's absolutely fine for many applications. Even COVID, if you see in airports, once you like back in the peak of the COVID period, when passengers were being screened in and out of busy public intersections, especially in Western countries, this was happening a lot. And also, I think China was one of the pioneers of this technology. When you exit in and out of metro stations and all the major public entry and exit points, they had cameras, and what they didn't in Bangalore airport in the Indian context, they had these kind of models where you try to when you get near the camera, the model is trying to identify where your face is, and it's putting a bounding box around your face, and then it's trying to also predict your temperature. So what is the temperature you have? It's without any kind of physical touch. It's trying to measure your temperature. These are wonderful use cases. But what if for that matter, how do you solve these problems? Let's say with respect to a self-driving car. I want to take this example for a minute with everybody. Imagine we have a use case like this. Imagine that we are trying to build a use case of a self-driving car, and how do you think a self-driving car will see the world around itself? This is what a self-driving car will see, right? So self-driving car will typically see the world around itself in this manner. So it has a camera that is mounted on top of the car, and this is the view that the self-driving car will see. It is basically trying to draw exact boundaries around the objects. It's not enough to just draw rectangular bounding boxes around a person, a traffic light, another car, because it will be inaccurate, right? Imagine it will be pretty inaccurate. If I simply end up drawing rectangular, bounding boxes, it will be pretty inaccurate. So instead of drawing, rectangular bounding boxes, how can I go back and instead, go back and draw exact boundaries around the objects. So if I see a person, I want to draw exact boundaries around what the person looks like. If I see a car, I want to draw exact boundaries around how the car looks like, something of that sort. So I want to draw exact boundaries around, let's say, how the person looks like, how the car looks like, and so on. So that's the whole idea of what we are primarily trying to drive here, basically, right? So that is the basic idea of this thing. Now moving on. So this is basically the use case where segmentation comes in handy, because if I put a bounding box around the person and it is a little inaccurate, let's say the pixels or the boundaries of the person are not correctly identified, then the car might hit the person. Okay, this is one use case where segmentation is absolutely crucial, where you cannot tolerate that error. See, this is not a dog actually, but the model says there's a dog here. Not really. But I want to be very clear. I want to be very, very specific as to the boundaries of the dog. So these kind of sensitive models, segmentation becomes very important. Okay. And another use case could be in the world of medical science, healthcare. Healthcare is another space where I think AI, ML, and has revolutionized healthcare. I'm sure you've gone through a lot of modules in your courses with us until now, and different instructors in different live sessions would have talked about these cases. AI in healthcare, especially radiology, X-rays, pathology, there's a huge scope of artificial intelligence in healthcare. Computer vision models are very actively used in the healthcare space. We talk about some of the top companies in the world, GE Healthcare, Siemens. That is, these are some of the biggest companies in the world who are providing hospital equipments for medical imaging, X-rays, CT scans, MRI scans. So how do you let's take an example where you take a picture of an X-ray, or you take an X-ray of a person's body, right? And let's say this person has suffered some kind of internal wounds. Let's say this person has been injured in a battlefield, or this person has been injured with some bullet wounds in the person's body, and an X-ray of the person is taken to understand where the bullet wounds actually are, and there is shrapnel inside the person's lungs or something of that sort, right? Let's say you want to identify the exact positions where those things are. You just don't want to draw a bounding box, a big rectangular box that, hey, I think this is the X-ray and this is where I see the object of interest. Not really. But what I really want to do is I want to find out specifically where that object of interest is. I don't want to just draw a bounding box around the object and say this is, but I want to know specifically, and explicitly where that particular object of interest is. I want to draw the exact boundary around the object. So this is the use case behind understanding why segmentation is action. So I hope the general big picture idea is clear. So localization and object detection are the general things that we have when we are drawing rectangular boxes. And segmentation also, we are questioning the where is the object in the picture, but in segmentation we are drawing exact boundaries. Okay, so that's the overall context, and we will come back to segmentation in the next week. So this is the part where we talk about segmentation next week. We'll talk about two different types of segmentation, instance and semantic segmentation, and this is how we start. So as I said, localization is more about identifying with respect to single objects, what object is there in the picture and where is the object in the picture. So that is primarily what we are trying to do in localization models. So we are doing two things. A, we are trying to figure out what is the object in the picture and where is the object in the picture. This we are doing with respect to single objects. Whereas if you look at object detection is something that we are trying to do with respect to multiple objects. So once again, object detection, we are saying that with respect to detection, we are saying that where are the objects in the picture. So this is a detection model that we have. So we are saying that, hey, where are the objects in the picture, and finally, what are the objects in the picture. So this is what we are trying to do with respect to object detection. This is with respect to multiple objects. If you see a fruit basket right now, so one part of what we are asking is, where are the fruits in the picture, and the second question will be that, hey, what are the fruits in the picture. So that's how we are facing object detection. Okay. So this is what we are doing primarily. We'll take some time to understand the localization problem. We'll do a proper hands-on here. So it involves answering the where and the how. So how do we build this? Now let's come to the architecture. Let's come to the architecture, and straight away from there a proper hands-on, which we'll do over the course of the next 15 to 20 minutes. So how do we build this thing? How do you build this particular rectangular bounding box, and how do you go back and classify that to an elephant? So what are we actually trying to do? Let's try to understand that a little bit more architecturally. Okay. The kind of models that we have done so far involved doing this, where this is what I talked about right in the beginning of the class, where you take the picture of an elephant and you pass that elephant through the convolution layers, convolution layer 1, convolution layer 2, convolution layer 3. You take the picture of the elephant and you pass it through multiple convolution layers, and what you end up getting at the very end is a feature map. This is what we understand, right? So feature map is the features of the image, the features that are extracted of the image. I repeat again, we take the entire picture of the elephant and we pass it through multiple convolution layers, con1, con2, con3, con4, con5. And what you end up getting at the very end are the features of the image. The feature map is what we kind of end up getting. And what we get After that, what we include after that is the feature, the fully connected layer. The FC layer is the part where we are trying to use a fully connected dense layer to do the final classification. This is pretty much what we have built so far. And now we can debate and discuss that either we can have convolution layers that we can add in ourselves, or we can also use a transfer learning based model. We can either add our own convolution layers, or we can go back and add a transfer learning based model where we can say that we want to use a pre-trained model, a ResNet model, or an inception net model, or a VGG net model, or some other kind of architecture we can go back and use, and based on that we can implement the whole thing. So that is one way we can go back and write this, right? So this is pretty much what we have seen. I hope people are all comfortable with this basic idea. So remember, once again, convolution layers are primarily acting as feature extractors. You take that unstructured image data and you're extracting the features of the image. You're getting the feature map, and now you're taking that particular feature map, you're flattening that entire feature map, you're passing it through a dense layer, dense of 5 or dense of 10, however many number of classes you have, activation equal to softmax, and right at the very end, we will end up getting the 5 or 10 different class probabilities. And the model will predict that particular class where the probability of occurrence is the highest. Okay, so this is pretty much what we have seen until now. Okay, this is the normal classification part of the problem that we have solved. I hope everybody is comfortable. Now, mind you, in object localization, we are doing one additional thing. What is that one additional thing that we are doing over and above identifying what is the object in the picture? We are also trying to answer the question, where is the object in the picture? And this is the part where we are doing regression. This is the only additional part that we are actually trying to. So over and above the classification part, which is absolutely fine. So we take that picture, we pass it through the convolution layers, we extract the features of the picture. And using those features, we are trying to, on one hand, we are trying to estimate the class probabilities. So we extract the features of the picture, and then we are trying to estimate the class probabilities there. And the second part is we are using the features of the picture, and then we are passing it through dense of 4 to get the bounding box coordinates XYWH. That is the regression part that we are trying to do. And this can be a transfer learning based architecture also. As we discussed, it can be a ResNet, Inception net, mobile net, any of the architectures we can go back and use. But the important part of the learning here is that a localization model or a detection model with a single object, it involves two different models in the same. We will build a classification network, which is something that you already understand, and we'll also parallelly build a regression network. Okay. Now let's try to take a slightly deeper look in terms of what is this XYWH. What do we mean by the XYWH? So just to quickly give you a little bit of context with respect to how we understand the bounding box structure. And before that, very quickly, just to give you a little bit of context in terms of what the coordinate axis basically looks like. This is how the overall coordinate axis thing looks like right now. And just remember, in the field of computer vision, the coordinate axis always basically starts from that origin, the top left. Unlike normal problems where the coordinate axis always starts from the bottom left, in computer vision problems, the origin always starts on the top left. The origin is always in the top left. And typically, increasing x-axis this side, increasing y-axis this side. This is just one important thing to keep in mind. So whenever we are discussing about bounding boxes and other kinds of things, just keep this at the back of your mind that whenever we are discussing about computer vision problems, the coordinate axis always starts from the top left corner. Yeah. No, a few specific reasons, sir, is just that when we are, I think the only reason I can tell you is that when we are drawing pictures, primarily we will say that we typically start drawing from the top left. Think of it that way. It's less like when we are writing text on a screen. When you're writing something on a computer screen, we are always doing it from the top left. So it's always from left to right and top to bottom. So that's the intuition basically. So that's why it always starts from the top left corner. So that's the intuition, right? So once again, this is the width of the rectangle, and this is the height of the rectangle. So next time when we look at the nomenclature of what is a W and what is a H, we'll typically understand the W to be the width of the bounding box and the H to be the height of the bounding box. This is typically how the terminology will look like. And also, oftentimes we can also look at this terminology. We can say this is the X initial. I'll just call it. This is the X axis, Y axis, correct? X initial, Y initial. And this is the X final, Y final. And will typically say that W is nothing but the width of the rectangle is nothing but X final minus X initial, and the height of the rectangle is nothing but Y final minus Y initial. That's a typical nomenclature that we actually introduce. Okay. So the width of the rectangle is given by X final minus X initial, and the height of the rectangle is basically given by Y final minus Y initial. And typically the origin will start from the top left corner. So this is the origin is somewhere here. So this is always the increasing x-axis this side. This is the increasing y-axis this side. That's how we understand the general convention that we define for object localization and object detection from a problem. Okay, so that is one thing to keep in mind. So so next time when we look at this particular architecture, once again, just to clarify, what are the key things that we are trying to learn? So one, we give the image as input. We pass it through convolution layers. It can be a transfer learning based architecture. And we're getting the features of the image. And from those extracted features, we are going back and trying to predict the class probabilities on one hand, and we are also trying to predict the bounding box coordinates on the other hand. So that is the thing that we are trying to do. And if you see the bounding box coordinates, we are trying to learn the XYWH. We're trying to learn the XYWH. Okay. And if you look at the XYWH right now, XY basically stands for the top left is basically XY. That's right, sir. The top left is basically the X initial, Y initial. The top left is basically X initial, Y initial, and the and the width and height of the rectangle is basically the the bounding box, the width and height that we talked about. So once again, so this is nothing but the bounding box thing that we talked about, and the width and height is nothing but the W and H of the bounding box, width and height of the rectangle, and this is the X and Y that we talked about. So we start. So all that we require, all that we go back and require is so all that we go back and require is basically the initial starting points. The X and Y are the initial starting points. The initial starting points are X and Y. These are the initial starting points we are looking at, X and Y, and we're looking at the width of the rectangle and the height of the rectangle. So the initial starting points are this, and we are looking at the width of the rectangle and the height of the rectangle. That's the basic idea. Okay. Now, how many outputs are we getting from the model? Let's see that. So we are basically getting total as many number of outputs as there are number of classes in classification. This we understand because remember in the classification architecture, right at the ending layer we put dense of 10. Let's say if it's an MNIST kind of example, we'll use dense of 10 because we have as many number of classes, outputs as there are number of classes. If there are total 30 classes, then we'll basically put dense of 30. If there are 20 classes, then we'll put dense of 20. So we'll have as many number of outputs as there are number of classes. If there are total 30 classes, then we will kind of use dense of 30. So right at the output layer, we will try to find out the probability of each and every class. So probability of one class, probability of two class, probability of three class, and we'll go all the way till probability of 30 class. So every single output corresponds to the probability of each and every classes. So that is one thing that we do. And on the regression side, we are basically getting 4 numbers as the output. So regression side, we are basically estimating 4 numbers. So X, Y, W, H is what we are trying to find out. The regression side, we are trying to estimate primarily 4 numbers, which is the X, Y, W, and H. So classification, we are trying to primarily, find out total, like we're trying to get as many number of outputs as there are number of classes. And regression side, we are basically kind of getting 4 outputs which correspond to the 4 numbers that we have right now. Now, what about the loss functions? There'll be 2 types of losses because there are 2 different networks. The classification part, we will typically look at a categorical cross entropy, a typical loss function that you've all studied so far. And the regression part of the architecture, we'll have an MSE kind of a loss, again, a different kind of loss we will have. Because ultimately there'll be some actual outputs. So there's some predicted outputs and there's some actual output we will also have. Then there'll always be some labeled data also we will have right now. So the classification part, we will try to compare with the actual classes, and we'll compute a cross entropy loss. And on the regression side, we will basically compare the predicted bounding box with the actual bounding box, and we'll basically get something called a predicted, we'll get something called an MSE loss. So based on this particular picture, the model predicted the bounding boxes here, but the actual bounding box is somewhere here, and based on that, we can once again compute another kind of loss. Even that we can go back and effectively perform. So that is what we do generally as part of the detection kind of model architectures, right? I hope all of you are able to get a sense of this thing overall. How do we well, there's got to be a way to combine the two losses, obviously. So we're not going to be dealing with the two losses separately. So one key learning that we have had in all our sessions typically is that the gradient descent that will happen eventually will happen on the basis of a single loss. I think until now we're able to understand that there are two different architectures. One is the classification part, one is the regression part. On the classification part, we calculate cross entropy. The regression part, we calculate MSE or MAE. But there's got to be a way we are able to kind of combine these two losses into a single loss. And what we do there is we basically kind of combine the two losses into a total loss. This is the classifier loss, categorical cross entropy. The regressor loss is MAE. And we try to somehow combine these two losses into a total loss. And we do a weighted summation. Okay. Now, what is the basic intuition behind the weights? What is the basic idea or the intuition behind the weights here? So we'll typically say 20 times classifier loss plus 1 time regressor loss is the total loss. So when we are calculating the total loss is nothing but we are adding 20 times the classifier loss, and we are adding 1 times the regressor loss, and we are getting overall total loss. Total loss is what we are getting in the process. So we are taking 20 times the classifier loss, plus we are adding 1 times the regressor loss, and we are ending up getting what we call the total loss. The overall loss is what we are getting in the process. That's the intuition of what we are getting. So the classifier loss is there, the regressor loss is there, and this is the total loss. Now, what is the basic idea behind 20 times classifier loss plus 1 time regressor loss? What is the basic intuition there? So the basic intuition there would be we are kind of, to think of a scenario where we are kind of taking 20 times the classifier loss, plus we are taking 1 time the regressor loss. I repeat, we are taking 20 times the classifier loss, and we are also taking 1 time the regressor loss, and then we are calculating the total loss. That's what we are broadly doing. So overall, one intuition here would be that we are focusing more on the classifier loss, because ultimately when gradient descent will happen, we will try to minimize the total loss. The total loss is what we are ultimately trying to minimize. Okay, so whatever formula for gradient descent we have seen, we are mostly trying to work with the total loss. And in that entire total loss that we are calculating, we have the highest contribution of the classifier loss. That means net, we are trying to give more focus on the classifier part of the architecture. And that is also true, no? I mean, if you think of it conceptually, that's also very true, that when we are trying to build object localization or object detection models, we are actually trying to focus more on the the what part than the where part. The what part is much more important. Imagine that you have a picture of an elephant, and you're trying to identify where is the object and what is the object in the picture. So let's say that that's the problem that you're kind of trying to solve. So one thing that we can do is we can so one thing that we can go back and do is we can identify so we can go back and identify the we are trying to identify the where part, the what part. The what part is significantly more important than the where part. It is very important to identify what is the object in the picture, and that is much more accurate. That's much more important to do. We need to be able to go back and identify what is the object in the picture, and then the next part will be the where part. So where is the object in the picture part? So the what part is much more important. It's because it's okay if the bounding box is slightly inaccurate, but it is not okay if you incorrectly predict the elephant to be instead you predict it to be a dog. Okay, so that is why we do a weighted summation and we calculate a kind of like a total loss. Okay, so this is the general idea. I'll be getting a little bit deeper into how we measure these losses, and I was talking a little bit about classifier loss and regressor loss, but how do we actually measure the accuracy of this kind of a model? We use something called IOU. So what we're looking at right now is a measure to identify the accuracy of our localization model. And as I told you that the specific part on classification we can identify using the accuracy. The classification accuracy we can obviously see. This is the loss function. I hope you understand that there are two different things. One is to measure the loss of the model. This is during model training. There are two parts to the whole equation. One is during training the model. We look at classification loss, which is entropy. We look at regression loss, which is the MSE. And then we calculate a total loss. The total loss is nothing but a weighted summation that we do. And we also talked about that the classification part of the architecture will get a higher weightage because we are trying to classify the objects with with higher weightage. The classification part is more important. So after the model is trained, after we have trained the model, now we are trying to evaluate the model. How do we measure the model's performance during prediction time? When we are testing the model with new data or with testing data, so how do we go back and evaluate the model then? So how do we go back and evaluate the model? Measure the model's performance during predict time, during model prediction time. So how do we go back and do something like that? So accuracy can be used for classification. So model predicts is an elephant, but in reality something else. So that we can always look at accuracy like the way we have learned that we can do. We can also, for the regression part, what we will do is we'll use a slightly different metric. And this metric is what we call IOU, intersection over union. And this is how we used what we use to evaluate the accuracy of the regression part of the algorithm. There are two bounding boxes we have. So one is the predicted bounding box. This is how we evaluate models in testing data, right? In production data, this is how you evaluate models. So so the model gives you some outcome, and you're now trying to kind of check that whatever the predicted box you're getting, is it closely matching the actual box? Okay, so what you do here, you look at the intersection area. Intersection area is basically what is the intersection between the actual and the predicted. So look at the entire intersection area. So what is the intersection between the actual and the predicted? And you look at the union area. Union area is the entire area that comprises of the actual and the predicted, and you divide the two. So that is how we define IOU. So IOU is a very good estimator of the accuracy of your localization model. So whatever bounding box that we are forming, so whatever a bounding box that we are forming, IOU is a very good measure of the of the overall accuracy of your bounding box. The model predicted that the bounding box is somewhere here. Actually, the bounding box is somewhere here, and IOU is a great measure of the overall accuracy of your bounding box. So we can look at the intersection area. The intersection area is the area in between. So that is the intersection area. The union area is basically the entire area on the orange, the pink part that we're getting. It is the yellow divided by the pink. So IOU is nothing but the A by the B. That is how we define the IOU. So we have the predicted bounding box, the actual bounding box, which is, you can already see they're a little separate. And the intersection area is the yellow one, and the union is basically the red one. So we take the yellow one, we divide by the red one, and we get the IOU. Okay, so typically. And if it is a very small value, that means the predicted is very far away from the actuals. And if IOU is equal to 1, that means the predicted perfectly overlaps with the actuals. Imagine if the IOU is equal to 1, that means the intersection and the unions are actually equal. That is the intuition. So that is exactly what we want. It will never happen in practice, but if we are able to predict the bounding boxes here, and the actual label data, the bounding box is also there, that's a 100% accurate model, which is again very hard to have. And the IOU value for that kind of a model is equal to 1. Just that for the regression part of the architecture, we cannot directly measure accuracy. So that's why we rely on IOUs to evaluate the performance of the model. This is the range of a couple of examples I've given you to understand IOU a little better. Once again, remember, IOU is used to measure the accuracy of your regression model's performance. Okay. So all of you see if you're comfortable. Any questions up to this point? Just wanted to do a quick check with the audience. Hi, Piyush, please tell me, sir. Yeah. Yeah. Go on, please.
Actually, how we can identify them? Could you please go to the previous slide?
Okay, sure. Yeah. Okay. Yes.
This. So, how we can identify means by this ML program, which is the actual box and which is the predicted.
Just to clarify, Piyush, the actual box is something that will anyways be part of your label data. I'll come to the hands-on, but just to give you a little bit of context, what happens is whenever you're labeling your data, just like what you did in classification. Let me ask you this question. Let's say in the classification part, the predicted object is an elephant. So the model predicted the object to be an elephant. That is a prediction.
Yes.
The actual object is also an elephant. The actual will always come from the label data. There will be a data label that you will also have. So that is how you can measure. So similarly, even for the regression part, the model will predict something. The model will predict something on the basis of the bounding box coordinates and all that. The model will predict something. The model will predict, okay, the object is probably somewhere here, and then the actual will be something. The model will predict that yes, the bounding box is somewhere here, and the actual will be something also. The actual will be part of your label data.
Right. My question is on real-time basis when because for this purpose definitely there should be a camera.
Yeah.
Right. So if we identify something kind of animal or human or face or whatever, so first what it will do means first it will draw a box of actual or predicted. Actual.
No, it will be predicted only. It will be, see, you have to understand, Piyush, one quick thing. Exactly. See, so two things. One what I want to clarify. What we are looking at here is the model training. So first, the two things. Okay, what you are saying, what you just now told me right now was basically model prediction. How is the trained model being used in the real world? I'll come to that. So let's say you already have built a localization model. Let's say you already have that model installed in your smartphones, and next time you open up your camera and try to take a picture, a group photo, what it is trying to do is it is first putting the bounding box. It is first drawing the bounding box. It is doing the prediction. During the model, whenever you are using the trained model in the real data or in the real-time data using the camera, as you rightly said, it is simply doing model prediction. There is no actuals there. It's always predicted there. So it is simply, so based on whatever trained model we have, we are simply trying to predict, because this is now a trained model. So we have the picture, we are passing that picture, that camera picture that is what we captured, we are passing that picture to the convolution layers. And we are basically predicting, okay, this is what I think the class is, and this is where I think the bounding box is. It's a complete prediction that we are doing in the real world. The real world, we don't even know what the actuals are. Fine? Yeah. So the actual part is only coming in during model training, sir. And just to answer your question once again, where will the actual come from? The actual will come from your data scientists. They are the ones who are labeling my data. So we will basically tell the system that, hey, pictures like this are elephants. They're actually labeled as elephants, and the elephant is present somewhere here. We draw a bounding box. Again, we'll give it one more object. We'll say, hey, pictures like this are basically dogs. The class is a dog. The actual class is a dog, and the dog is present somewhere here. We draw a bounding box. The actuals. We are providing the actual labels. So we are giving the machine lots and lots of XY combinations, XY, 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 and the machine is learning on the basis of that. Next time there is a new picture, the model will classify, okay, this is what I think that object is, and this is where I think that object is, and this is how I measure how accurate that particular model is. The predicted is this, the actual is this. Fine. So this will only happen on your test data, so not the real data. Real data, we don't even know the actuals. This will happen on your test data. Yeah.
Just a little bit more advanced topic. Because we can't understand yet. So
no
the
problem,
thing is,
but then it's good that you're asking questions, sir.
Yeah, the thing is, because once question came in mind, later on, if you will not ask, then we can forget. Right? So,
no, that's a very good thing. Very good thing. And I absolutely appreciate that you ask questions along the way as you go. I have no such hard and fast rule that you pause your questions. I'm a big believer that absolutely, whenever you get questions, you should be asking. Absolutely fine.
And another thing, suppose means it is just about 2D.
Right.
Because we are identifying image, kind of a picture. But in real time, like in healthcare, if you identifying tumor or something like that is a 3D object. Is there any option also that we can train our model in 3D and then we can?
That's a very good question. Actually, first of all, when you talk about healthcare and specifically if you talk about X-ray data and all that, it's actually in a slightly different format called a DICOM format. It's again a little different thing. You talked a little bit about 3D. Let me tell you, images, generally speaking, are like the particular pictures that we generally deal with, whether they are surveillance photos, whatever kind of pictures that we're dealing with primarily, they're mostly 2D pictures. Now, although we represent them as, okay, let's say if I look at 100 cross 100 picture, The width is 100, the height is 100. It's a 2D picture. But we still say it is cross 3. The cross 3 only stands for the channel, but the picture is still 2D. That's why I think in all your computer vision residencies, you actually use something called a con 2D, because the dimensions of the picture is ultimately 2D.
Okay.
So we're looking at a 100 cross 100 picture. 100 is the width, 100 is the height. It's a 2D picture. The cross 3 that we typically use is only for the channel, red, green, blue channel. Now, to answer your question, what do we do when we have 3D? Let's say we have, especially it comes in, especially for videos that comes in. So the question could be, how do we handle videos? Let's say, for example, we are using 30 FPS or 60 FPS, something of that sort. We're looking at something like a 30 FPS or a 60 FPS or something like that.
Yes.
What is the meaning of 30 FPS? 30 FPS means in 1 second video, there are 30 frames.
Yes, moving.
30 frames means 30 images.
Yes.
Imagine that we are trying to use gesture recognition, which is a very interesting use case. So the use case would be somewhat like, let's say if I, let's say Upgrade starts this reactions, feature, where if I, put a reaction, a thumbs up reaction, the reaction will be automatically sent. So if you have used something like a Cisco WebEx, WebEx actually has this feature. Teams doesn't have it. Google Meet, I have not seen it yet. Zoom doesn't have it. But Cisco WebEx is a platform where they actually have gesture recognition feature, where you can start your webcam, and if you make a particular gesture, it automatically registers the thumbs up, a thumbs down, and a clap, and a raise hand. It recognizes 4 gestures, gesture recognition. So what it basically does is it captures that entire video sequence of 2-3 seconds. And if you consider 30 FPS, then in a 3-second video, there are 90 frames that we are capturing. That means there are 90 images that we are capturing. So the dimensions of the image now become 90 cross 100 cross 100 cross 3. Each and every picture is 100 cross 100.
Right.
And now it becomes 90 cross 100 cross 100. So what we do in that case, Piyush, we actually use something called the con 3D. Now we have a 3-dimensional image. So in that case, we use something called the con 3D. Just like we have primarily worked with con 2D until now. So especially when it comes to higher dimensional inputs like this case, especially videos and other medical data sets and all, we use something called the cons 3D.
Okay.
So in Keras, there is something called the cons 3D also that you can use. That's one way you can do it. The other way you can also do it is using a combination of LSTMs. LSTMs are again a bit of a different topic, but the other alternative way how you can handle and solve that problem is you can use LSTMs. You can basically take a sequence of many pictures, and that's another thing to process it. LSTMs can also be used in a different way. Yeah.
Right. Definitely, this AI part of this artificial neural network is very interesting, but it is simultaneously it is also a little bit advanced, so need to understand.
Absolutely, absolutely. I think once the foundations are clear, it should be, which is why these are the foundations we are looking at. I think we'll see a hands-on. Once the foundations are clear, it should be a lot simpler to digest. Yes, yeah. But keep asking lots of questions, sir. Yeah, yeah.
All right. Thank you.
All right.
Thank you.
All right.
No, you can mute me also.
No problem. Yeah, sure, sure. Yeah. I think you cannot mute yourself anyway. Is there a way you can? Okay, I think. Okay, let me just quickly. I'll do that. Yeah. Saravanan, there was a question you had also. Is IOU used in training phase? What is the difference between IOU, between regression loss and IOU? Well, I would say IOU is more like used in the, in the model accuracy, the evaluation phase. I would say so. Training loss is something that we are using at MSc. Yeah, it's more of a way to measure model accuracy. But you can alternate actually. IOU can also be used in the model training as well. We have to write a specific function to calculate that, but we can do that absolutely. Yeah, but generally accuracy MSc is what we can use as a loss function, and IOU is more of a measure that we use to evaluate the the overall accuracy of the model. Yeah. See, I'll tell you, Saravanan, the only thing is when we talk about loss now, the lower the loss, the better it is. If you look at the entire architecture of gradient descent always looks to minimize the loss, isn't it? We are iterating over many epochs and we are trying to minimize the MSE. So the very nature of a loss function is that we are always trying to minimize it. But if I consider IOU as the loss, the problem is you don't want to minimize IOU, you want to maximize it. That's the thing. So we have to customize it slightly. We cannot directly use the IOU metric for a loss function. Because the nature of how deep learning training always works is we are always trying to iterate through many epochs, and we are trying to minimize the either the cross entropy or the MSE loss. We are always trying to minimize our loss function. So the best model is that model where the loss is minimized. But in this case, what will happen is if you minimize IOU, then you might end up with a very bad model, because IOU we want to actually maximize, not minimize. So we have to actually change that metric a little bit before we use it. So whatever I explained here was mostly from a prediction perspective. Got it, right? So, okay. I hope this is clear to everybody. Small diagram that summarizes IOUs and everything that we've talked about. So again, you can very clearly see right at the very end, the predicted bounding box is here. The actual is also here. It's a perfect overlap. It's a good model. This is actually the worst model. The predicted bounding box is here. The actual bounding box is here. So there's absolutely no overlap. So we are saying this is a very poor quality model comparatively. So the predicted box is somewhere here. The actual box is somewhere here. So we are looking at a extremely poor quality model. This one is also, kind of pretty bad model. So the predicted box is somewhere here. The actual box is somewhere here. So IOU is 50%. So this is again a pretty bad quality model. And this is actually the predicted bounding boxes here, the actual bounding boxes here. So IOU is 25%. So again, overall, this is the best model because the predicted is actually similar to the actuals. All right, now we'll come to some hands-on. Enough of some theory. We'll look at some hands-on. And typically, these are the data sets that we have for object localization. These are some of the most popular data sets that we use for object localization. Until now, our journey has been restricted to classification, and I think with respect to classification, we have mostly seen ImageNet datasets. ImageNet has been one thing that we have seen, but with respect to localization and detection and also segmentation problems that we study next week, we'll primarily look at these datasets along the way: Pascal, Vogue, IIIT, Oxford-IIIT dataset, and COCO common objects in context. The one that we will do in our session right now is the IIIT Oxford-IIIT dataset. So this is so the name IIIT and Oxford are used is because it's a collaboration between two universities, the IIIT University in India and the Oxford University. So the collaboration has been done to prepare this particular data set. So data preparation is one of the most important components in machine learning. I hope everybody understands and appreciates that as well. So the data preparation is actually a very important aspect, because if your data is not right, then the models will not be right. So data preparation is actually an extremely important component of what we are trying to do in machine learning and deep learning. Because if your label data is not right, if your label data is not proper, then the models that you eventually end up building will also not be proper. So it is very important to have the right amount and the right kind of label data. Because as I said, if your data is not right, if your labeled data is not right, then your models will also not be right. So it is very important and extremely crucial to have the right kind of label data for your modeling purpose. That's one way to do that. So many of these data sets, just like ImageNet, have been formed through university collaborations. A lot of universities have come together, they've collaborated, and many of these data sets have actually come up in that particular, sprung up in that particular fashion, rather, I should say. Yes. All right, let's move on. Now the whole thing is, how do we prepare our data for, how do we go back and prepare our data for model training? So what is the method that we use to prepare our data? So all this while I was discussing that, we prepare the label data. I think all through classification also you had some label data given to you, obviously. So we had some kind of label data that was given for us already. So in other words, the classes were already provided for us. The pictures like this are elephant class, pictures like this are cat class and all that. So similarly for object localization, we have to also prepare our data. So what is needed in this particular case? We need three things. We need X, Y coordinates, right? We need X and Y. So in all of machine learning, we require some X's and some Y's. So we have to provide the system with lots and lots of XY combinations, XY, 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 XY. So provide the system with lots and lots of these so-called XY combinations, and let the machine learn on the basis of all these XY combinations. Right? I repeat again, you provide the system with lots and lots of these so-called XY combinations, XY, 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 XY. And the whole idea is the machine will learn on the basis of these XY combinations. So next time there is a new X, the model will predict some Y. Okay, so we'll provide the machine with lots and lots of these so-called XY combinations. Once again, XY, 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 so and so forth. You provide the machine and the model will learn on the basis of that. So what is needed? What is the X and what is the Y here? So what is that input X and what is the output Y here? I'll come to that, Saravanan. I'll give you some references along the way. once I step into some hands-on from Kaggle, I'll get into that. So the X is basically the image. So we need the image. X is the image that we have. And what is Y? Y is basically the classification label and the bounding box coordinates. So these are the two things that we require. So if we are trying to prepare our data from scratch, not like we are given some pre-built data set already, and somebody's already given us some data, in prior, and we are simply using that. Not really. That's not what we're discussing. We are actually saying that if so we have some images. Images in this case will be the pictures, and the outputs will be basically the classic. On one hand, we will have the classification label, and on the other hand, we'll have the bounding box coordinate. So that's what we will basically have. So once again, images are basically the pictures that we have, and the classification labels and the bounding boxes we have. So that is what we will have here. So once again, so on one hand, we have the images. Images are the X's, the inputs, and the outputs are the Y's will be the classification labels and the bounding box coordinates as we call it. So this is pretty much what we have right now. These are the XY combinations that you will typically feed. So I repeat again, these are the XY combinations that you will typically feed in overall. All right. So how do we prepare our data in the real world? In the real world, data preparation can be done using lots of different types of tools. We can use some open source tools. I think mostly in our sessions or the assignments or the exercises, or even if you go to Kaggle, any kind of competition websites, typically your data will be given to you. Like in most of your cases, we have already given the data for you. We have already told you that, hey, this is the kind of data that you're working on. But in the real world, that will not happen. Real world, nobody will give you the label data. Oftentimes, when you're starting or embarking on a project from scratch, you will have to go back and prepare your own data. Okay, so in this case, as you can see, the data is already kind of going to be given most of the time. So we will give you the data. We'll tell you exactly what type of data we have and all that stuff. So data will be kind of given to you. But as I told you, in the real world, when we are solving real problems, then nobody will tell us what type of data set is there. So we'll have to go back and figure out our own data. So we'll have to actually go back and kind of label our own data and all that. So we'll have to do that ourselves. That is the very important part once again of deep learning, where you have to prepare your own data. So if you're working in whatever sector, let's say if you're working in healthcare, as Saravanan was asking, oftentimes you'll have to go back and you'll have to label the X-ray data yourself. You have to actually go back and take those X-rays. You have to tie up with local hospitals, and you're the person who will have to manually go back and take those X-rays and try to label those X-rays as, hey, X-rays like this correspond to cancer, and X-rays like this don't correspond to cancer. So oftentimes the label data will have to be prepared by somebody like you. Okay, and a lot of time and effort is typically spent in the overall data cleaning process, the data labeling process. Oftentimes this is a step which is very underestimated. I think when we are solving deep learning, machine learning problems, we often underestimate this step because we take it for granted. Like especially while studying the topics, most of our exercises, everything is given to us. Like somebody tells us that, hey, this is your X and this is your Y. Just use this data, build a model. But this is the most important component where you will actually have to spend a lot of time, collecting your data, labeling your data. So you'll actually be spending a tremendous amount of time in this particular part. Okay, just wanted to further, clarify and reinstate, kind of more of like re-emphasize that particular point that data labeling will be a very important part of your day-to-day work in any organization. Because in the real world, data will not be prepared, data will not be ready, data will not be in the format that you want, and you will have to spend a tremendous amount of time and effort in labeling your data. Okay, and typically for object localization, different types of open source tools can be used. So we can use something like a LabelImg. So this is the Python installation that you can use, simple one, where you can install the Python library, and you can go back and you can basically draw bounding boxes around the objects. It's just like you drag and drop using your mouse, and you say, hey, objects like this correspond to a person, objects like this correspond to a ball, objects like this correspond to a cat. So that's how the data labeling will be done. Oftentimes there are a lot of platforms also that we have. So we have some freelancing platforms and all that we can use. Oftentimes companies will rely on certain types of freelancing platforms also, where they will typically try to allocate the work to certain freelancers who will typically do this work. This is mostly low-skilled work. So we are looking at mostly low-skilled work where a lot of expertise is not required. So as I said, we are looking at mostly low-skilled work where too much of expertise is kind of not required. So that is one kind of role that we are looking at, and we can oftentimes hive it off to the set of freelancers who can get it done for you. It's almost like at the start of the thing, you're given a set of pictures and you're asked that, hey, like, right at the end of the day, I want you to label these pictures for me. You have to tell me that, hey, pictures like this are this, pictures like this are this, pictures like this are this. You have to go back and label all these pictures in a certain way for me. So that's how the localization models will work. Okay. So we can also use other kinds of platforms. You can also install and try LabelImg. You can use pip install LabelImg to try it out. You can also use other kinds of platforms. I'll give you some references. We'll circle back to this later on. But then, in case people in this audience are trying to do something at an enterprise level, in case in your organization you're trying to start and pioneer projects from scratch, you can look at companies like Appen.com. Appen is one of the pioneers in data labeling space, and they're an organization whose entire business is built around data labeling. They're not doing anything else. They're only doing data labeling, and they have partnerships with companies like Amazon, Microsoft, Google, Adobe, LinkedIn. So all these are organizations they partner with, and their entire business is on data labeling. But all that they try to do is they provide the organization's label data. So next time you look at an Amazon Alexa and you see that you say something and Alexa responds in a particular way, mind you, Alexa has to be trained with tremendous amount of label data. Somebody actually has to have, would have taught Alexa that, hey, when I say something like this, you should do this. Whenever I say something like this, you do this. So somebody had to have trained Alexa on those different types of speech patterns. And that particular training data is coming from the hundreds and thousands of freelancers that Appen actually employs. Appen is a platform, so where a lot of people can sign up, they can work on part-time jobs, flexible jobs. And these are the kind of people, the entire army, the background workforce that is providing the label data that is powering all the, the devices around us. So the job roles can be something very straightforward. So, you can look at one simple example job role. I'll just show you, it's very interesting. As I said, most of the time, what we do is, we only focus on the, the glitz and glamour part of machine learning. But this is actually the real, the real difficult parts of ML that where people are actually involved. And I wanted to focus a little bit on Appen and what kind of stuff they're doing. So this is Appen's LinkedIn page. All of you can take a look at it. This is Appen's LinkedIn page. Sorry, I think. Yeah, there goes Appen's LinkedIn page. All of you can see. I'll click on Appen and I'll click on the jobs section very quickly. And you can take a look at what kind of roles that they're hiring for. So very interesting. You can see data collection. So they've got good jobs as well. Not that every job is like manual data collection, not really. But if you mostly see most of the jobs that Appen has, see data collection, English language in India, work from home. And the moment you see this kind of work roles, data collection related work, you can say that this is mostly the kind of work that is related for with respect to what we are doing. Okay, data collectors, you can see any Chinese language. And this is mostly for NLP kind of thing that they're looking for. Data collection, English in India, work from home. You can go back and take a look at this role probably. And you can see what kind of work you're looking to have. And you can also look at what kind of overall expectations they have. Okay, overall. So all that you will be required to do in these kind of roles is you'll be basically probably given a particular you'll be particular shown a particular transcript. So they will send you a particular transcript to read, and they are basically testing out the speech to text models basically. So next time you have a particular, you say something, the model will automatically convert it to text. We've all seen that, right? Google Assistant, we can say something and Google will automatically convert it to text. How do you think these things work? So somebody would have had to train this model on tremendous amounts of input-output combinations. Who are providing the data? So platforms like Appen, the hundreds and thousands of freelancers working on Appen, they are providing this data. So they are providing the platform with lots of label data. So they are telling that, okay, patterns like this correspond, when the text is this, the speech is this. Okay, when the speech is this, the text is this. When the speech is this, the text is this. Okay, so when I say this, the corresponding text is so and so. When I say this, the corresponding text is so and so. Next time when I say this, the corresponding text is predicted to be so and so. So they are the ones who are actually providing the label data. Okay, this is just a small thing I wanted to clarify. And Saravanan, you were talking a little bit about the healthcare space. You will actually see a wide range of use cases. And at Appen, you will actually have a very good resources with respect to healthcare data also. And you can actually also start to see what other types of problems that they are solving. NLP and speech is one thing we can look at. Computer vision, the topic of our interest right now, we can start to see image annotation is what they also do. So you can see create annotations, image annotation jobs like polygons, dots, rotating bounding boxes, and so on and so forth. So next time you're wondering that, hey, Sayan, how do we go back and how did we label our data? So so where are we getting those actual labels from? Those actual labels are actually coming from platforms like Appen, where you're giving a particular picture and the freelancers are basically labeling that, okay, pictures like this correspond to apples, pictures like this correspond to elephants, and this is exactly where the elephant is present. So this is what is happening inside these kind of platforms. Okay, you can also use some open source tools for data labeling purposes. I will go back and quickly, give you a little bit of rundown on the different data preparation steps and quickly run you through this part, and then we will come back to the hands-on over the course of the next 5-10 minutes. The hands-on example will take some time to run because it's so welcome to the world of advanced computer vision. So no longer basic CNN models were actually pretty fast comparatively because you are only doing classification. But now that we are stepping into localization, we are running two parallel models, regression model and the classification model. It will be a lot slower, so it will take a lot more time to train. So we'll actually keep some time aside for the model training. Just to give you a little bit on brief in terms of what we are trying to do. So we'll download the tar file, the zip file, we'll extract it to disk, and we'll basically extract out the images and the annotations. This is the part that we will do. So we'll already be provided with this particular data. So IIIT Pets dataset is what we'll work on, and we'll take the data from the website, and we'll already be given the images and the annotations in this case. So we'll not be creating our data. In this particular case, we'll already be taking our data raw from the website. Okay, images will be the normal images, whatever image structure that we have, PNG, JPG files we will have. And the annotations will be basically the bounding boxes that will already be given to us and the class names. Okay, so remember we require XY combination. So this is exactly the XY combination that will be provided. Images is the X and annotation and the class labels are the Y. Annotation is nothing but that particular bounding box coordinates. Okay. So just to clarify, this entire information will be present in an XML file. XML is a very, very popular file format that is used typically for representing the annotation information. Annotations basically consist of two things. The annotation is nothing but the Y coordinate, whatever Ys we are looking to predict. And in this case, the Ys are nothing but the class labels and also the bounding box coordinate labels. So what is the actual class label and what is the bounding box actual, excuse me, bounding box annotation. So we get that in a XML file, and we store all the XML files info in a single CSV file. This is the part that we will look at. I'm just discussing the entire architecture with all of you, the entire flow of steps actually. We'll do that, extract the data, we'll take the images, annotations that are separately there. We'll store the entire information into a single CSV file. We'll write some scripts there. And finally, we'll visualize some image and annotation combinations. So whatever you're seeing right now is until the training data. So whatever data is basically given to us. So this is what you're seeing on your screen right now is the entire training data. So the entire training data is actually provided here right now. Okay, and finally, we will go back and build a batch generator. This is the part where we start to do our training in batches. And now we'll go back and build the object localization model. So until here is just a data preparation part. You take your data, download your data, take the image annotation combinations, which is present in one XML file, right? And then you store all the XML info into one CSV file. We'll see that. We'll visualize our training data. We'll see how the bounding boxes look like. And finally, we'll build the batch generator. And this is the actual modeling part where we'll use a ResNet 50 model. It's a pre-trained model that we will use. This is the part where you take the picture and you pass it through a CNN to extract the features of the picture. Add some custom layers, probably the batch norm and the flatten and all that we will do. And finally, we will use one part for classification, dense of 37, because there are 37 classes we have, and the other part for regression, dense of 4. And then we'll combine the two losses into one single loss. All of you recall. So weighted addition we will do, and we'll take one final loss. And this is how the whole final model will look like. There'll be one input and two outputs. Okay, this is the network that we'll try to build, and we'll look at augmentation examples also along the way. Let's see that. Let's now come to the example, and let's look at the let's go back and take a look at the data preparation part and the entire end-to-end use case of how we are. And mind you, localization is with respect to a single object. Detection is with respect to multiple objects. The ideas remain exactly the same. So once we are done with the example of localization, then we'll come to the architecture of detection. But their ideas are exactly the same, actually. All right, this is our data set, IIIT fetch data set on which we'll run localization on. So first, I will change my runtime to GPUs because I need hardware accelerators to run this example. It's already set on Colab. We'll quickly take you to IIIT fetch and show you what this data is all about. 200 images per class is actually, I think, is a good question, but a lot depends on the kind of data that you have actually, Saravanan. I think I think the number is less important. What is more important is what type of data you have. So because we are dealing with animals are very distinctive attributes. If this was something else, other types of objects, it would have been harder. But because animals are very easy to distinguish based on certain types of attributes, it's actually easier. So that's one way to look at it actually. So 200 is fine enough for this particular exercise, but we can definitely try it out. But it's relative actually. There's no hard and fast rule as to how many images you require per class. But the whole idea is you need to have a good representative set of features, and also you need to also have a good amount of augmentation done. Augmentation anyways we'll do. That will anyways do. Okay, so let's move on. Let's try to get going. And we've got 37 classes, and you can see there are 200 pictures per class. And this is the annotation data that is already available. You can see this is the data set and this is the annotations. These are two sets of files, X's and Y's. Okay, the Y's will basically contain the bounding box labels. This is segmentation. You can ignore the third part. Third part is something we'll come back to next week. But for the time being, the images will contain the pictures and the annotations will contain the bounding box coordinates. This will be here in XML file. Okay, XML file will basically contain this information. So simple enough. So let's quickly head over and download this data. We'll quickly use wget utility to download our images.rgz and annotations.rgz, which is available here. We just try to download these two things. You can see the links that are coming. We're using wget utility to download these two sets of files that are already available. And then we will go back and ensure they are downloaded here in the directory. And then we'll go back and simply unzip the tar files. Straightforward. That's what we are doing initially. It is simply zipping and unzipping that we are doing. Just downloading and unzipping the files that we are doing initially. And then we'll just quickly take a look at one of the files and understand whether the annotations are correct. If the data is properly downloaded, we'll just quickly do a validation in a minute. Right, looking good. And I think we'll quickly go back and explore some of the images and annotation combinations right now. So the directory right now should have the downloaded annotations thing, downloaded images. You can see these are the downloaded images, downloaded annotations. We can obviously go back and look at it from the folders themselves. I can expand the images folder, I can expand the annotations folder. We can quickly take a look at some of the sample pictures that we have here. And you can see the XMLs are actually present in annotations. XMLs are going to contain the bounding box information. And I'll quickly show you what a typical XML file contains. And we'll focus on the very first picture, Abyssinian. All of you can take a look at it, Abyssinian1.jpg. This is the cat, okay? Abyssinian is basically a cat. So this is the picture, the image that we have right now. And you can see Abyssinian is basically a cat that we are seeing in the on the screen. That is the cat that we are able to see. So we have that particular image, and what we are doing is we have that particular image, and we also have the corresponding bounding box information for Abyssinian1. So we have the image. Image is coming from the JPG file. And if I go to the XML, the corresponding XML, the XML name will also be Abyssinian1.xml. We'll quickly come to that. the Abyssinian one.xml. I'll quickly open up the XML here, and we can see the XML how it looks like. All of you take a look at it, please. This is the corresponding XML how it looks like, and we should be able to understand this a lot more better. Look at this, all of you. The corresponding image is this, and the corresponding XML is basically this. It tells you a couple of things. One is the file name, the folder name. It tells you a few other metadata information. The size will tell you the width and height of the picture. That's the 600 plus 400 plus 3 picture. And this is the part where the main the bounding box information is actually present. XML is nothing but it's a markup language. So obviously the markups are present. A BD box, bounding box, you can see. So you can see xmin, ymin, xmax, ymax. That means starting right from the top left corner, we have xmin, ymin, which is 333, 72, and xmax, ymax would be 430, 425, 158. So as long as I know the two corner coordinates of a rectangle, we can draw the entire rectangle. I think mathematically all of you can relate to that. If I go back and look at the two corner, so if I can go back and look at the two corner aspects of the rectangle, we can effectively go back and kind of entirely draw that whole rectangle. So that's one thing that we can go back and do, as long as we can identify the whole thing around this rectangle. So as long as we are able to identify the two corners of the rectangle, we can find out the complete rectangle, as we have done in this particular case. Can we use JSON instead of XML? You actually can. Technically, there's no problem. In any kind of structured data, if you have Saravanan, you can absolutely use it. But XML is a very extremely popular file format in that case. So I think that's one of the reasons typically why we prefer XMLs. But definitely, technically, if you have a JSON data as well, let's say this may not always, you can absolutely use that. But then many of the computer vision libraries and all that we are talking about that we're using right now, they mostly use JSON they mostly use XMLs, and they prefer using XMLs. XMLs are preferred, and the reason being that it is supported by many of the existing packages and function calls that we do down the line. Yeah. So XML is kind of, I would say, preferred, but doesn't mean that you cannot use JSON. You can use JSON also, but JSON may not be inherently supported by many of the packages and all that. So you need to convert it to XMLs to make it work. Yeah. But otherwise, technically, whether you have an XML, whether you have a JSON, ultimately you'll try to convert it into a CSV file and then work on it. So technically, you can have any file format. So you can still work on it. You will also see here also we'll eventually convert it to a CSV. So what I'm referring to is that many of the predefined scripts and many of the available scripts that we see, XML is a more popular file format. But yeah. All right. So this is what we have: the corresponding image and the corresponding annotation. This is the X-Y combination that we have right now. Right now, the data is there in two different sources. We need to kind of combine them into one single page. So we need to basically put this entire information into one single CSV file. And we need to store that, hey, this is the picture. So whenever we have pictures like this, the output is predicted to be Abyssinian, and the bounding box coordinates are predicted to be so and so. Actual bounding boxes are actually so and so. This is what we have right now. Now, please remember, some of you might actually have a question that the Sayan we talked about XYWH. In case you have that at the back of your mind, please remember that this is nothing but the WH coordinate part. So if you see, so the bounding box is coming out to be this one. So this just to kind of draw this out for the whole picture. We can see this for the whole picture right now. So we can say that, hey, this is the entire bounding box. So this is the X min, Y min. This is how the bounding box will look like. It's actually only around the cat face. By the way, we are not looking at the entire cat body, primarily on the face of the cat, actually. So mostly the bounding box will come somewhat like this. And we'll say the X min, Y min is this one. There goes X min, comma, Y min. And there goes X max, comma, Y max. And this is the width of the rectangle. And what we are looking at here is the height of the rectangle. Okay, so we have x min, y min, top left corner, x max, y max, bottom right corner. This is the width of the rectangle, height of the rectangle. So x max minus x min will be the W, and y max minus y min will be the height. This is just how orientation how it looks like. So actually, while we are modeling, while we are solving the problem, in the code we will try to convert it to W and H. We will not exactly solve for x max, y max, but we'll basically try to find out the x min, y min, and the W and H of the rectangle. So as long as we find out these four numbers, this part is not required. We don't need this part actually, because as long as I know the starting coordinates and the width and height, I can actually find out the ending coordinates also. And once I know either of this information, I can form that entire rectangle. Okay, so that is just one other way to look at it. So just remember, as per convention, many of the files and many of the pre-treated data sets that we get will typically contain the bounding box information like this. Okay. All right, this is pretty much what we have. We can look at some sample, examples also. And the next thing that we are doing is we are using a predefined Python script to kind of convert this data into a CSV format. I repeat, we are simply going and converting this data into a CSV format. I have a script that is already provided. This is provided by TensorFlow. So before that, I'm going to quickly connect onto my Google Drive and access that particular script. This is the part where I mount my Google Drive on Colab. I hope all of you have heard of these things, mounting the G Drive on Colab, because you're trying to access the Google Drive link. Let me quickly do that. So all I'm trying to do is I already have a script called generate dataset.py. What will this script do? This script will basically take the entire information and it will convert it to CSV. So right now I've got images in one place, annotations in one place, labels in one place. All are there in different places. And this is typically what is going to happen in the real world scenario also. You might have a particular folder where all the pictures are there. You might have a particular folder where the annotations are there right now. This is how you will typically maintain your data in the real world also. Okay, so I've got a predefined script that we have given, which will simply convert your entire data into one single CSV format. And the CSV file now will look somewhat like this. So this is what your entire CSV file will basically look like. All of you can look at the screen. This is how the whole CSV file will look like. Okay, every single row corresponds to one image or one training data or one training image. We are looking at the file, the location of the file, where the file is present, images, main code, images, main code, images, main code. So this is the images folder, and you can see the location of that particular image. That is the X, and the Y is going to be the X min, Y min, X max, Y max, and the class level. Okay, so that is how the whole thing is basically present. Okay, so these are the bounding box coordinates, and this is the class label. So the only new thing that we have basically done is we have added a label encoder part here. The label encoding part is done, 0, 1s, and all that. That's the part. Okay, straightforward. So all I've done is I've taken the information that is present in two disparate folders in a completely unstructured format. I've gone ahead and I've just kind of converted the entire data into a structured format that looks somewhat like this, where you're looking at the table, and every single row corresponds to one picture, and we're looking at the the images and the output combinations. The X's are basically the file, and the Y is nothing but the bounding box coordinates and the predicted class labels, the actual class labels for that matter. Okay, straightforward. How many classes do we have? We've got overall 37 classes, all the way from class 0 till class 36. You can see. So we have main cool, Japanese chain, Egyptian Mao, all the way till American Pit Bull Terrier. These are all the different classes that we have right now. And if I want to display some of the pictures with the bounding box, I can just go back and see what this will look like. Okay, all of you can see the screen. This is the Samoyed. Samoyed is basically a dog, and you can see that how the whole annotation part kind of looks like. This is a real label data. So what you're seeing on your screen is basically the real pictures, how they are. So you can see that given this image, the image is given, and the annotations are basically the class, what class of dog it is, and what class of where the bounding boxes actually are. We can look at one more example. The image is basically this one, and we are looking at what class it is, Siamese, and what is the bounding box, it is somewhere here. You can look at one more example, Control Enter. So we can see that this is a Scottish Terrier, and the bounding box is present somewhere here. So what you're looking at in your screen right now are actual labeled data. Okay, actual labeled data is what we are observing. So this is the British short here, and you can see the bounding box coordinates over there they're given. And this is the kind of data that people at Appen and all the data labelers will typically label. We'll talk quite a bit about data labeling and how it is practically done in the real world. So this is going to be a very challenging task. Imagine that you hire some freelancers and pay them like a certain amount of money every hour. And this is the kind of work that they will be doing. So they'll be looking at each and every picture and they'll try to classify what class that particular picture belongs to, and also the bounding box coordinates with respect to that particular picture. So that's how the whole thing will work out. If you look at the code is pretty straightforward. We are using a library called OpenCV. CV2 is the OpenCV library. And these are mostly functions. No need to worry too much about the other parts. These are mostly functions that we have used. And all that we are trying to do is we are trying to draw a rectangle. So first we are reading the image IMRead. So train df is the data frame that we had here. This is the file that we have, and we're reading that particular image. Image number is a random image that we have picked up from this particular file. So what is this particular piece of code doing? This particular piece of code is just picking up a random number. If I just run this code np.random randint, if you just look at this particular code np.random randint, what it will do is it will basically pick up any random number from 0 all the way till the number of rows. Because shape 0 will tell you the number of rows, right? So 0 till, I think we've got how many rows? Let's see. Training data, I think we have got, the shape of my data is how much? The shape of my data frame, we can see. The shape of my data frame is 2984 training data. And now when I say 0, I'm basically looking at 2984 rows. That's the integer which I'm outputting. And all that we are trying to do is we are trying to go from 0 till 2984, and we are choosing any random integer from 0 till 2984. Actually 2983 exclusive. So we are choosing that integer 26986. We can randomly choose once again 578. This is the index number that we are basically choosing. Any integer from 0 exclusive of this value. Simple. So let's say we are choosing the integer 1999, and now what we'll do, that is the image number. And now what we'll go back and do is we'll go back and we'll read the image from that particular index number in the image, and we'll simply draw the bounding box on the basis of the coordinates x min, y min, x max, y min. This is the OpenCV syntax that we have used primarily. Okay, now OpenCV basically works in a BGR format. So all that we have done is we have converted this to an RGB format. That's it. So because Matplotlib can render things only in the RGB format, that's all that we have done. Rest is all simple Matplotlib functionality that we have used. Yes. That's a very good question, Mr. Jagdish. So it's a beautiful question that you asked, sir. I think just to touch base upon that a little bit. I think platforms like Appen, they have got. So oftentimes it's a very good argument. Actually, you can actually say that, hey, Sayan, who is there to guarantee that whoever freelancers you've hired, are they even doing their job correctly? It's actually a very good thought. Because imagine, start of the day you're given dogs and cats to label. Anyways, it's useless, boring work. Who will do that work? I mean, so what is the check that actually somebody is doing that correctly? Let's say you are, and this is actually how it is. It might sound funny, but actually this is the work. So the start of the day, we'll give you 100 pictures of dogs and cats and different types of animals, and all you have to do by the end of the day is you have to go and label those pictures. So what is the guarantee that somebody who is least interested in the work simply goes and labels everything to be dogs? Okay, or simply goes and randomly labels everything to be cats. Chalo, kaam ho gaya, khatam, everything is done. That's it. Not really. We cannot do that, right? Because I'll tell you how Appen prevents these things from happening. So we basically call it human in the loop approach, where whatever data annotations we are giving, there is actually the machine which will take 5% of your data and try to validate that whatever data you provided is right or not. See, if a project is completely starting from scratch and you have to put in some effort, let's say you're starting the project entirely from scratch, then you have absolutely no label data. But Appen is basically at a stage right now where it already has some pre-trained models available. Think of it that way. So let's say over the last 1 month, you've already been gathering data. So you already have built some pre-trained model. At Appen, they have already built some pre-trained model which they will use for data validation. So let's say out of 100 pictures that you're labeling by the end of the day, Appen will take 10% of those pictures. They will take 10 pictures and they will try to use their own trained model and try to validate that whatever labeling you did, was it correct or not. So Appen thinks the label should be so-and-so, but you labeled it to be so-and-so, so you're penalized for your work. Something of that sort. There's a lot of checks and balances even in data collection as well. This becomes a bit of a challenge when you're starting to collect data from scratch. But I would say when you're doing things from scratch, what happens is intuitively when you're doing things from scratch, then you have to put in more extra efforts. But typically at the data collection part as well, we'll have models that we use to validate this. Yeah. Jagdish, I can hear you, sir. Hello. Just a minute. I think I was speaking. I just you raised your hand. I just unmuted you. Hello. No, I'm not able to hear you, sir. Actually. Okay. Is there anybody else able to hear Jagdish? Or is it only me? Sorry. No. Yeah, Jagdish is not audible, I think. Yeah. We're not able to hear you, sir. You can type, yes. Sure. Let me know, but it's a very good question that you asked actually. But the short answer to your question, just to summarize once again, is you basically have checks and balances at the data collection site. People who are labeling at Appen. Appen is basically an entire platform. So not only that it will hire anybody and anybody can label anything, not really. So at the end of the day, whatever task you complete, your payments will be linked to that. Appen will already have validation models built in at their end. They'll be mostly pre-trained models and all they already have available. And based on whatever label data that you're providing, Appen will also do their own validation using their own pre-trained models actually. Yeah. How is the output? Well, the green box is not predicted, sir. What I'm showing you right now is only the training data. I'm actually yet to come to the modeling part. The modeling part will be completely here. This I'm actually yet to show you. This will come to right now. What I'm showing you right now is just the training part. Whatever data is available right now. So whatever data is available to you right now is just this part. So what I'm showing you right now is just the input-output combination. The picture is this, and the output is predicted to be a main cool, and the bounding box is predicted to be somewhere. Actual bounding box is somewhere here. That's it. Okay. So coming to the modeling piece, this is the main model that we are actually building. You can actually see the screen now. This is the pre-trained model that we are first loading in. We are using the code to load in a ResNet 50 model. You can see tf.keras.applications.resnet50. Include top equal to false. Input shape equal to image size, comma 3, and weights equal to ImageNet. So we are loading a pre-trained ResNet model. And very important, we are saying include top equal to false. So what is the reason why we do include top equal to false? More of a technical question I'm asking. What is the reason why we do include top equal to false? Any thoughts? Anybody? Why do we do this include top equal to false? So why in practical learning do we do include top equal to false? More of a general question for the audience. So why do we go back and do include top equal to false? Okay. The include top equal to false is primarily done because if you look at ResNet is primarily used for is already a pre-trained model that is trained on ImageNet. Again, it's a general transfer learning concept. I'm actually touching base on a very general transfer learning concept. So when we say include top equal to false basically is done to ensure that you're going ahead and you're dropping the dense layer, the output dense layer. So let us quickly see what happens when we set it to true versus when we set it to false. So typically, whenever we are implementing transfer learning across the board, even in your classification modules, you would have seen that whenever you use any transfer learning architecture, like a ResNet, VGTNet, InceptionNet, MobileNet, whenever you use any of these architectures, we will always use include top equal to false. So what is the reason why we do that? Because when we say include top equal to false, let me just load this model again. So this is the ResNet model with 175 layers. You can see it is already built in. And if I quickly show you the model summary, you'll be able to see the model summary looks somewhat like this, where we are starting off with a 224.3 input, and we are passing it through the entire ResNet architecture. And the ResNet architecture right now consists of convolution, max pools. This is the entire ResNet built-in architecture that we already have. So this is the entire built-in architecture that ResNet already has, all of you are able to see. And you come all the way down, you can see how we are also continuing to shrink the picture. We start off with a 224, 224, 3 picture, and we're continuing to shrink the picture. We're continuing to shrink the picture, half it, half it, half it, half it, half it, go all the way until we touch 7 cross 7 cross 2048. We touch this zone. Actually, 7 cross 7 cross 512. This is the part where we touch right now. So this is the final featureized picture that we end up getting. So isn't this what we are trying to do in CNNs? CNNs are primarily used for that reason. So convolutional neural networks, convolution layers are primarily used to extract the features of a picture. We start off with a completely unstructured image right at the outset, and we continue shrinking the picture, shrinking the picture, shrinking the picture until you end up getting a 7 cross 7 cross 512 picture at the output. This is what we end up getting in CNNs primarily. But if I had gone and done include top equal to true, because now the good thing is that I can add my own layers, right? Isn't it? We've taken the whole picture and we have kind of extracted the features of the picture. We have featureized that picture, which is what convolution layers in transfer learning are used for primarily. Now that we have extracted the features of the picture, now we can add our own layers. We can add our dense of 10. You can add our dense of 5, and so on and so forth. Okay, but if we had not done this, if we had simply done, let's say, include top equal to false. If I had not done that, if I said include top equal to true, if I had done that instead, if I include the top layer, then let's see how that architecture looks like. Let's see that. Let's see that now. See, I'm loading the data once again. This will be a slightly bigger model because after that 7 cross 7 cross 512, you see more layers will get added here. After the 7 cross 7 cross 2048, more layers will get added. And if I look at the model summary now, see there are 177 layers for the change. There are more number of layers we have, obviously, because we have added 2 dense layers at the bottom also. So once again, we are starting off with a 224, 224, 3 input, which we understand. We are all able to relate to that. We're starting off with a 224 cross 224 cross 3 input. And we are passing the machine through multiple convolution max pools, convolution max pools, convolution max pools. So we're doing that. We're going all the way down. You're shrinking the picture until you touch 7 cross 7 cross 2048. This is that 7 cross 7 cross 2048 that we're getting. This is the final thing that we're touching, 7 cross 7 cross 2048, the final convolution layer that we had. This was up to 175 layers that we learned. And the moment you say include top equal to true, I have added 2 additional dense layers, 1 max pooling and 1 dense layer. You can see this is the 177 layers we're getting. And we can see the final thing is dense of 1000. This dense of 1000 is done with respect to ImageNet, because ImageNet is basically trained with respect to 1000 classes. All of you know these are all pre-trained models, right? I think you have seen this in your convolution CNN module also. We have something called VGTNet, InceptionNet, ResNet, AlexNet, ZFNet, okay, GoogleNet, DenseNet. There are lots of different types of architectures that we have with respect to transfer learning. There are lots of different architectures that we have, and all these architectures are basically trained on the ImageNet dataset, which has 1000 classes. These are what we call pre-trained models that we have used all through transfer learning, right? And in all these pre-trained models, the output layer is always dense of 1000 because ImageNet had 1000 classes. But do we need this for our example right now? Not really. We don't need 1000 classes to predict them. So whenever we are doing transfer learning, we will never include the top layer. We'll always exclude the top layer because we want to add our own layers. We only want to use the convolution layers, whatever filters or whatever weights and biases we have learned, we want to only use that part. The final output layer is something we want to completely scrap out. Right? I hope this is absolutely clear to everybody. Why we go back and always do include top equal to false. So we'll do include top equal to false, and you will see the number of layers will reduce down to 175 again. Let's see that. This is the general transfer learning concept I'm talking about. Okay, 175. And if you look at the model summary once again, you will start to see that we are once again starting off with 224, 224, 3. And if you come all the way down, we're starting off with this particular picture. Dimensions of the picture is 224, 224, 3. And the output that we are ending up getting is 7 cross 7 cross 2048. Beyond that, we also had some dense layers that were coming. Now it is not coming anymore. Include top is, okay, it's actually called a top layer, sir. It's a convention. we call it the top layer because it's a top dense layer. It's not exactly the bottom, it's actually the top. Top means like, include top, like this, the top dense layer. Top is basically with respect to the output. That's the convention that they define, yes. Yeah. So, so imagine another intuition, Jagdish, would be, when you look at the hierarchy of filters or the convolution layers, the initial convolution layers always focus on the lower level features, the very basic features like lines, edges, curves, the bottom features. And right as you go through more and more convolution layers at the top, you look at more top level features. That's the other intuition. So as you take the picture and as you pass it through more and more convolution layers, you try to extract more top level features. So top always refers to the end in this case. Yeah. Okay. Next, now here we will add our own convolution layers. We'll see that. So first we are setting all the layers to non-trainable. And now we'll add our own layers. And this is what we are doing. So whatever output that we are getting, the 7x7x2048, whatever output we are getting, we will basically save that model output in something called X. So the output of the pre-trained model, we will basically save it in X. And then we will go back and flatten the X. Then we'll go back and add a dropout. We'll do a dropout to introduce some regularization to prevent overfitting from happening. So tf.keras.layers.dropout 0.5, add some dropout of X. And then we'll go back and add a dense layer, dense of 200 for some additional learning. And finally, do a batch norm. And these are the additional few steps that we've incorporated. All of you can see. So whatever 7x7x2048 we are getting on top of that, we are going ahead and we are doing a flatten. We are flattening that output. And then we are going and adding a dropout in the process, drop out 50% of neurons, then add a dense layer, dense of 200, and then go back and do a batch norm. And whatever resultant output we are getting, on top of that, one part we will drive for classification, dense of 37, and one part we'll drive for regression, dense of 4. So that is the thing that we are going back and trying to do here. Okay. So just to clarify, I'll quickly run this for you and then show you the summary. That will be probably a little better to understand. So just remember one thing that we have until now we have done till 7x7x2048. That is the pre-trained model that we have actually used. And if you look at the final model summary, the final model summary looks somewhat like this. Where we once again start off with a 224x224x3 output input, sorry, and we are taking the 224x224x3 input, and we are once again passing it through multiple convolution max pools, convolution max pools, convolution max pools. So we are shrinking the picture until at the very end we are getting 7x7x2048. We talked until here. Then we took that output, then we flattened it, if you recall. Then I told you we added a dropout of 50%. Then we added a dense of 200. These are the 200 neurons in the dense layer. And then we added a batch norm. So these are the 4 additional layers that we've added on top of the output that we are getting from transfer learning. And now whatever output we are getting in batch norm, whatever we are getting until here, one part of that we are using it for dense of 37, and one part of that we are using for dense of 4. So it's kind of like saying, so just wanted to draw this out and show you a little better. So all of you can look at the screen here. So whatever output we are getting here until this part. So you can see the output. So basically the step name is given by this batch normalization. So batch normalization is the name of the step. So whatever step we are getting, this is the input to this step. It's the same input we are getting in both the steps. You can see both the steps, the same input is coming. So that means whatever we are getting, taking the input image, passing it through the ResNet model, and getting that 7x7x2048, doing a whole lot of other stuff, batch norm, dense norm, all that, and finally we are left with that batch norm layer. This is the final batch norm layer we are in right now. And now we are using that batch norm layer. One part of that we are using for dense of 37 for classification, activation equal to softmax, and one part of that we are using for dense of 4 regression, activation equal to sigmoid. So dense of 37, softmax. We are trying to predict 37 different class probability softmax activation, and one part of that we are using for regression, which is dense of 4 sigmoid activation is what we are trying to do. So that's the intuition behind how we are running this whole thing. I hope this is clear, absolutely clear to all of you, and I hope it also you also appreciate why we went ahead and dropped the output layer, because so that we can add our own output layers, because we want, for our specific case, we have only wanted to use the output until here. So this is the part that we did transfer learning. So whatever weights and biases we learned, whatever filters we have learned, we are simply using the convolution layers to extract the features of the picture. We just trying to featureize the picture. and with whatever featureized picture we are getting, one part of that we are using it for dense of 37, one part of that for dense of 4. And once that is done, the final model, you can see we are trying to train the final model here. Optimizer equal to Adam. And there are two types of losses that we define. The code is slightly different. You might have seen a slightly different code in your prior sessions. The only new part that we're incorporating here is we're adding two different types of losses. So output name, we specify specifically for respect to reg output, the loss is MAC. And with respect to classification output, the loss is categorical cross entropy. We are defining two different types of losses. And we are also defining the loss weights. For the reg output, the loss weight is 1, and for the class output, the loss weight is 3, and the matrix is accuracy. So this is the standard thing that we are doing now, and we already talked about it, that we do a weighted summation. We'll not go back and directly add up the regression loss and the classification loss. We'll do a kind of a weighted addition because we are giving a more preference to the classification part of the network. And this is the part where we are training the model using the generator function, and this will take a little while to run. And I think at this particular point in time, we can also maybe go back and take a quick break, mid-session break. We've been going on for quite some time, 10:54 on the clock. We can take a quick break. The session will go on. It will extend for maybe another, maybe half an hour from scheduled time. I know we are scheduled to close at probably 3. Let me see the timing. It might go on till, 3.5 hours instead. So we might go half an hour, little beyond half an hour actually. That's the only thing. Yeah. So we'll quickly train this model. Here we need you 37 classes. What if the output can be more than 1000? No problem, Jagdish. You can please go back and update it. So see how we put dense of num classes, LE and num classes we have put. So we'll just update it accordingly. No problem. Update it accordingly. LE and num classes will take care of that. So if let's say you've got 1500 outputs, then you say dense of 1500, no problem. That is the way you change your architecture now. That is absolutely fine. Which is fine, which is absolutely okay. Ultimately, we'll know your outputs, right? That's the whole idea. Okay, so this is how the network is training. All of you can see. Just wanted to quickly show you the model training. There are model training also. There are a few things to keep in mind. ImageNet has only 1000 different classes. Absolutely right. Yes. ImageNet has 1000 classes. That's true. That's a standard ImageNet dataset. All the architectures, every single one of the pre-trained architectures that you have. You talk about AlexNet, ZFNet, ResNet, InceptionNet, GoogleNet, ResNet, anything, any of the architectures that you take, which have been trained on ImageNet. ImageNet has 1000 classes of different types of objects. Yes. Which is fine, which is absolutely okay. See, in this case, we have 37 outputs, right? But the 37 classes are very different. ImageNet was trained on different types of everyday objects, aeroplanes, cars, bikes, and all that. But right now, we are talking about pets. That is the whole idea of transfer learning, Jagdish. The number doesn't really matter as long as the pictures are representative. You will anyways do transfer learning. You will anyways retrain some of the previous convolution layers, right? So whether it is 1000 or 10,000 outputs will not matter. That is the whole idea of transfer learning. We're not starting from scratch. So although ImageNet was trained on 1000 different classes, but whatever classes we trained ImageNet on, here we are working on an entirely different data set. We are talking about pets. ImageNet was not trained on pets. ImageNet did have some examples of animals with it, but it was not trained on Samoyed dogs or short hair, white British short hair cats and all that. That is the whole idea of transfer learning, right? So the output classes can be entirely different. The number doesn't really matter, sir. It will work, absolutely. It has to be representative, but you need to retrain some of your convolution layers to make it work, I would say. Okay, and if you look at the model training right now, there are two different sets of accuracies that are coming. All along, we have only seen one type of accuracy. Now we'll basically get to see the validation classification accuracy also, and the validation regression accuracy also. You can see this is the validation accuracy for classification. It is increasing over the number of epochs. So classification accuracy right now has touched 89%, and the regression accuracy for validation has touched 78%. It was very low before. And we can also go all the way to the left-hand side, and we can see the try to reduce the zoom a little, and you can also start to see the classification, the training classification output accuracy, and the training regression output accuracy. So this is the training accuracies. So what you're seeing on your screen right now are the training accuracies. These are the training accuracies, and these are the validation accuracies. These are the validation accuracies. So here goes the training accuracy, 100%, 80%, and here goes the validation accuracy, 87%, 79%. So we can clearly see the classification part of my network is actually overfitting. So only on the, so we can analyze the individual parts of the network and decide what to tune and how to tune. So we can clearly see the classification part of my network, the one where we are trying to predict what class of object we have got, that is clearly overfitting. So 100% accuracy here, but only 90% accuracy here, overfitting. But the regression part is kind of underfitting. Let's say it's 79.96% accuracy here, or 80.94% accuracy here. So there's a scope to basically maybe add some regularization and batch norms and dropouts to reduce the overfitting on the classification side, and we can probably try to beef up the architecture using some dense layers and more neurons on the regression side. So this is some tuning we can do. One other thing that we can potentially do is we can try to rearrange the weights a little bit. Right now we have taken 3 parts of regression and 1 part of classification loss in the total sum. We can try to rearrange those weights a little bit and maybe give a slightly higher preference to regression loss so that the regression loss is also minimized equally. Okay. So this training will go on for a while. We are right now only at the 13th epoch, but I hope all of you are able to get a gist of what we talked about until now. At the very end, the training accuracy is touching. Once again, the classification part of the network has trained pretty well. You can see on the classification side, the model has trained pretty well. Even the testing accuracy is also quite good. I think it's touching around 88%, and the validation accuracy is touching around this one. But then, as I told you, there is certainly some amount of overfitting on the classification side that we can see. So potentially it would be good to regularize the classifications a little bit more, and regression side we can see some underfitting happening. Also, we understand that in Keras, what happens is typically the accuracy values will vary across multiple epochs. And how do you do that? How do you basically save the best state of your model? Anybody knows that? So in terms of code, in terms of hands-on, how do we incorporate it? How do we practically do that in Keras? How do we incorporate that? How do we make sure that we are able to save the best state of our model? Because at every epoch, what happens is, like typically, let's say after this, at this point in time, I've trained the model. I've done model.fit. So the code that I've used is final model.fit generator. If I just show the final model right now, the final model will nothing be the last epoch. Whatever weights and biases I've learned until the last epoch, the final model will basically be that. Okay. So whatever weights and biases I've learned until the last epoch, the final model will simply reflect that, the last state of the model. So that is the general idea. So now the question is, the last state may not be the best state. If you quickly take a look at it, the last epoch, the validation accuracy in classification is only 88%, but the validation regression is 80%. But actually, the previous epoch was better. Even if you compare with respect to the last epoch, the 19th epoch was better. Validation also was better, and regression also was better in validation part, right? So how do you save the best state of your model? How do you save the best state of your model? Because right now, what happens is I've already trained the model over, let's say, 20 epochs. And after 20 epochs, if I want to display the model, only the final model's last epoch's weights and biases will be saved, right? But the last epoch may not be the best epoch. You can very clearly see the last epoch. The validation accuracy is 88.59, and the regression output accuracy is coming out at 80.80%. But if you just look at the previous epoch, the validation was 89% in classification and 83% in regression. It's really better. So typically, whenever you are training deep learning models over multiple epochs, only the last epoch's outputs are really considered. Right? So the last epoch's weights and biases are really taken by default. But my point is, the last epoch may not always be the best epoch. So how do you go back and save the best epoch? What is that particular Keras method that we use to save the best epoch, and not necessarily the last epoch? Any thoughts? How do we save the best epoch? Let's say we have trained the model for 10, 20, 30 epochs, and we want to save the best epoch. How do we save the best epoch? Not the last one, but the best one. So we use something called model checkpoint callbacks. Have you heard of checkpoint callbacks in this audience? Any thoughts? So just a quick check. Have you guys heard of checkpoint callbacks? We use them we call them checkpoint callbacks. We call them callbacks in Keras actually. So we can use something called a model checkpoint callback, just to show you what a checkpoint callback actually refers to. So these are called model checkpoint callbacks in Keras. Callbacks are basically certain functions that Keras uses to save the callbacks are basically certain special types of functions. These are all the different types of callback APIs that Keras can use. You can see callback is an object that can perform actions at various stages of training. So during the model training, Keras can perform all these different operations. So right while doing the model.fit, you can call something called a checkpoint callback. And what will happen is during the model training, Keras will save the models. So if you're running the model for 100 to 20 epochs, like in this case, at every epoch, we will continue saving the models. We'll continue saving the different instances of the model. And then we will, the next time we run the epoch, we will only save that particular model with a higher accuracy. So epoch 1, we save the model. Epoch 2, we save the model. Epoch 3, we will only save the model with the accuracy higher. Epoch 4, we'll again save the model. So at every point in time, we'll keep saving the models over a period of time, over many, many epochs. And we'll only save the model where the accuracies are high. So checkpoint callbacks can be very popularly used here. Okay, you can see. Okay, so whether to keep the model that has achieved the best performance so far, and you can see that. So mostly you can monitor a particular kind of loss, and you can only save that particular model where the best has been achieved. There are other kinds of callbacks that you can also use. For example, Keras, we also have something called early stopping. Anybody can tell me what is early stopping? It's a more conceptual questions actually. What is early stopping? Have you heard of early stopping? Model checkpoints are an important concept. You must know this because this is important with respect to. It's a general deep learning concept. I think this is something you should be knowing already. This model checkpoint. What is early stopping? Anybody wants to talk about early stopping? I'm sure people have heard of early stopping before. What is early stopping as a concept? Avoid overfitting. Okay. All right. Anybody else? So early stopping is basically an idea that, let's say you're training a model for 20, 30 epochs. So a good example of early stopping is happening in our current context. It's a beautiful use case where it's happening. You can see that even if I'm training this model for more epochs, see, I've already trained this model for 20 epochs, right? And even if I train this model for 5 or 10 more epochs, I continue to train this model for, let's say, 5 or 10 more epochs, what will happen? There will not be any incremental improvement in the performance. Okay, I repeat, even if I train this model for, let's say, 5 or 10 more epochs, we will not be able to see any incremental improvement in the performance of the model. Incrementally, the model will not become any better. That is the intuition. Okay, so even if we go back and do this, incrementally, we will not be able to see any performance as we speak. Okay, I repeat again, incrementally, we will not have any general performance. So I repeat again, incrementally, we will not be having any performance. Incrementally, the model will not become any better. So that's one way to look at the whole thing. So I repeat again, incrementally, the model will not be any better compared to what we have before. So that's one way to look at the whole thing. Yeah. So you go back and stop at that particular point. So what we do is you go back and stop at that particular point. You go back and stop at that particular point where the accuracy does not improve any further. So what we basically go back and do here is we stop at that particular point where the accuracy does not improve any further. Okay, that's the intuition here. But I repeat again, you go back and stop at that particular point where the accuracy, the model accuracy does not increase any further. So that is the whole idea behind what we are primarily trying to do in early stopping. Early stopping means you continue training the model. You continue training the models over a period of time, and you continue training the models, and you stop a little early when the validation accuracy does not change too much. Right? In this case, you can see even if I train for, let's say, 5, 10, 15 more epochs, the validation accuracy does not seem to change, does not seem to get impacted. So we'll basically go back and stop at that particular point where the validation accuracy does not change too much. That's the intuition behind what we do as part of early stopping, right? Hope this is absolutely clear. Hope the audience is absolutely fine with this. Yeah. Okay, there is one more type of callback that is very popularly used in deep learning is something called tensor board. You might be seeing this later on in your courses. Tensor board is actually a wonderful visualization tool that we can use in deep learning to monitor the progress of our models. And you can look at tensor board in more detail later on. The tensor board can be used to go back and monitor the overall performance of our models. That's what tensor board can be primarily used for. It's more of a visualization API that we have. Anyway, so whatever model we have built right now, let's quickly take a look at the model predictions. What kind of predictions we are able to run out of it? I think I just went ahead and by mistake, I ran this code once again, which is okay. I'll just probably, stop this for a minute and let it run at the back end. And I already have a saved model, which I have here. Don't worry about this part. So I already trained the model, and then let's say I've already saved this model in the, and then we'll go back and evaluate the model. So I'll just train it for 5 epochs just to show you a sample performance, because I mistakenly hit this code. Let's see this. Let's run this for 5 more epochs and see how this works out. Yes, absolutely. I'll do that, Piyush. Yes, I'll do that, sir. Yeah. Actually, there is no easy way to know that, Piyush. I think that is exactly where some of the visualization interfaces will come in very, very handy. So the visualization tools will go back and tell us, we can monitor over many, many epochs at what point we're getting a ideal training and testing accuracy. There's no easy way to do that, actually. The short answer to the question is no, we cannot. We cannot do that. We cannot monitor this that way. No, we cannot. Okay, now that we have got the model up and running, let's save the model in H5 file, final model.save H5 file. We're just going to save that final model in the H5 file. And we're going to be using that model for making predictions very quickly. Let's see what kind of predictions we're able to make on the sample data. So this is the test data, and we can very clearly see that the classification part is actually working correctly. So in reality, we have a Keyshawn, and the model is actually able to predict the Keyshawn. We are able to see that right now. We're able to make a correct prediction. So we are able to, in reality, we have a Keyshawn, and in practice also we have a Keyshawn. So the predicted bounding box and the actual bounding box are a little way out right now, but we're able to see how the overall thing is working out. So the model predicted is a Keyshawn, actually also is a Keyshawn, and the predicted bounding box is here, the actual bounding box is here. We can look at one more sample example. Let us see how the accuracy is working out right now. Absolutely right, advanced GPUs to reduce the time. Yes, you can see the classification part is once again correctly happened. You can see the in reality we have a, we have a beagle. Model also predicted a beagle right now. In reality, we have a beagle, and model also correctly predicted this to be a beagle. And now we can easily see that the regression part is also pretty accurate. So not very accurate, but is able to reasonably give us that particular portion where It is correctly done. The green box is made by the yes. And you can do that one more example. Look at this one. This is the Persian cat. Once again, we're looking at another sample example. We can look at one more sample picture. And we can run this on a set of examples, and we can see mostly the classification part is correctly working. The regression part is a little wayward, but the classification part is mostly working correctly. There can be a few pictures we can see where it is not working correctly. Persian cat is again correctly coming. There can be a few pictures we can see where it's not correct, but as you can see here, the red part is actually the actual labeled box Jagdish. The green part is something that is the model is predicting. You see here it is a little wayward, but classification worked correctly. The model predicted this to be a Leon burger, which is accurate, but then the bounding box labels are actually inaccurate. See that right now. Okay, yeah. I hope this is absolutely right, sir. Yeah, red is the part which is the actual label, and the green is the classification label that they got. Okay. All right, wonderful. Let's move on. I'll be sharing this data set with you, and let's get going and look at some foundational ideas with respect to detection now. What is detection? Some of the history of object detection, and we look at some object detection architectures now along the way. So until now, we talked primarily about the classification scheme of things, where we look at a single object in the picture. And we try to primarily answer two questions: where is the object and what is the object? Now we are looking at detection, and only difference between localization and detection is that we are looking at multiple objects in the picture. Let's say we have an image which consists of two objects. Now all that we are trying to do is we are trying to figure out where are the objects in the picture and what are the objects in the picture. That is all that we are trying to do in detection. The foundations are exactly the same, the concepts are exactly the same, but we learn a few different types of architectures along the way. It's a little theoretical. I'll run you through some architectures, then we look at some pre-trained models and look at a little bit of hands-on. Okay. So the only difference between localization and detection would be that in detection, we are trying to do this for multiple objects. That is the primary difference. Now, how do we do this? How do we go back and do an object detection? Well, obviously, object detection is a more complex use case. And one central idea that we are trying to follow here is whenever we are trying to solve a complex problem is basically a combination of many simple problems. Okay, so think of it this way, that a complex problem is basically a combination of many simple problems. So that's the way we understand what a complex problem actually is. So object detection is more about finding lots and lots of bounding boxes. So it's like you're doing lots and lots of object localization every time. That's what we are trying to do primarily. So one thing that we have to do is it's like divide and conquer. So whenever we're trying to solve a difficult problem, what we try to do is we try to divide that particular problem into many smaller sub problems. That's one thing that we try to do. So when we try to solve some problem, we try to divide that into many smaller problems. That's one part of what we try to achieve. So we try to divide that entire problem into many smaller sets of problems overall. That is broadly what we are trying to drive even in this particular exercise. So when we are solving a simple problem, we are trying to divide that problem into many smaller problems. So first things first, what we do is we take that entire data. Okay, so this is the entire data that we have right now. All of you are able to see. This is the entire data that we have right now. Okay. So I repeat again, we have the entire data. This is the complete data that we have here. And we are trying to go back and break down that entire data into multiple pictures. So this is the complete data that we have right now, and we are trying to break that entire image into multiple sub-images, sub-pictures. So and then and all that we are trying to do is we are trying to do object localization on each and every one of these sub-pictures. That's the idea. So from one image, we are trying to create many sub-images. So we use some different algorithms for actually doing that. So there's certain approaches that we will see how we can perform that different operation. How we can take that that main picture and we can divide that main picture into multiple sub pictures. And then the whole idea is how we take each and every one of those sub pictures and how we go back and do localization there. Because again, this is one entire object detection problem. So we are trying to take that main picture, We are trying to use some logic to divide that main picture into different sub pictures, or what we refer to as ROIs. ROIs stand for regions of interest. We're taking that main picture, we are dividing the main picture into different ROIs. ROIs stand for regions of interest. And then on each and every one of these sub pictures, we are trying to do object localization. We are making a very important assumption in the process. The assumption that we are making is we are assuming that each and every of these sub pictures contain exactly one object inside it. That is a very important assumption that we are actually making. Just to clarify, we are making an assumption that each and every one of these sub pictures, it consists of exactly one object inside. That is the main assumption that we are actually making in this process. So assume, so we are making an assumption that there is exactly one object that is present in each and every individual picture. So we're taking the main picture, we're dividing that main picture into multiple sub pictures. Okay, we're taking the main picture, we are dividing the main picture into multiple sub pictures, and we're making the assumption that each and every one of the sub pictures or ROIs consists of exactly one object inside it. And now on each and every of these sub images, we are performing object localization, divide and conquer. So whatever we have learned all this while, we are applying the same principles just that on multiple different sub pictures. That's the basic idea of this. So for example, we take this main picture. How many ROIs do we have? Right now we have divided this main picture into 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 regions of interest. We have taken that main picture and we have divided that main picture into, as you can see, 9 regions of interest. We have divided the main picture into. And now we will take each and every one of those, we'll take each and every one of those, we'll take each and every one of those regions of interest, or ROIs as we call it, and then we'll go back and do localization on that. For example, we'll look at the middle image. We'll look at this particular middle part of the dog that we can see. We'll take that particular sub image and we'll perform localization only on that. So we'll look at that particular sub image and we'll try to figure out that, hey, what is the object in the picture and where is the object in the picture? We look at another sub image and we try to figure out, hey, what is the object in the picture and where is the object in the picture? We already seen this, mind you. In the last exercise we did, we already seen that. The only difference is we take the main image, break it up into multiple subparts, and then on each and every subpart, we do object localization. And finally, we look at another sub image and we try to figure out what is the object in the picture and where is the object in the picture. So that's the problem that we are trying to solve. The object in the picture is background, and where is the object in the picture? It is XYWH. That's the problem that we are once again specifically trying to solve. Okay, so this is what it is, and each and every new image is called an ROI. As I told you, it's called a region of interest. So we take the main picture and we divide the main picture into what we refer to as regions of interest, and then on each and every regions of interest, we perform localization. We try to figure out where is the object and what is the object. Okay, all right, wonderful. How to create ROIs from the image? Now the obvious question that, so we already know the second part. So once the ROIs are created, we know how to do localization that we already learned. We can take that picture and we can pass it through CNN, extract the features, do regression, do classification. We are good with that. Now the interesting part is, how do we actually create the ROIs? So this is the part where we will look at a few different types of architectures. We have lots and lots of different types of architectures that we have that actually help us create the ROIs. This part is a little theoretical. I'll try to give you some context, some references to the module also. But there are different types of ROIs we have. There are different mechanisms we have to create the ROIs, and we'll see what those different techniques and mechanisms actually are. We'll see that very quickly. Okay. So how do we create the ROIs from the image? So let's explore the different architectures that we have here. Is it possible any further error when we will connect all the parts of that image? Not really, because Piyush, what we will do is we'll remove the overlaps. All right. So we look at different architectures now, and very quickly, the most basic architecture that we have is the RCNN-based architecture, and we're looking at a very different family of models right now, which are referred to as region-based CNNs. And this is just to give you a little bit of history on the architectures and where it started from, how it started from. We're looking at something called region-based CNN kind of models, or RCNN-based models. And why do we call it region-based CNNs? Because this is entirely convolutional neural networks on the basis of regions. We are looking at the different regions of interest, and then we are basically doing localization. So this is what we call RCNN-based model. And the very first algorithm that we had here was what we refer to as selective search. You can see we use selective search to identify the ROIs in an image. That is what we basically did. So the first of the steps that we used here was we kind of use selective search to identify the different ROIs in an image. And then we basically went with the rest of the operation. So one very important concept with respect to RCNN based model was take the main picture, we divide the main picture into ROIs. Now, what approach did we use to do the ROIs? We use something called selective search. Right? So we create 2,000 different ROIs from each and every picture. So we create thousands of ROIs from each and every picture. And then out of that, we only select those ROIs where the probability of object is very, very high. So selective search is basically a very static algorithm. It's a non-deep learning algorithm. And it's again, a very old technique that I'm talking about right now. Just to take you through some of the history of object detection architectures that we had. So selective search is where we started our journey effectively from. And the whole idea was it was able to take a particular picture as input, and it was able to give us so by taking a particular picture as input, it was able to tell us, it was able to return the different, it was able to return the different bounding boxes. It was able to return the different, overall. So by taking that particular picture as input, it was able to return to us the overall ROIs or regions of interest as output for that particular picture. Okay. So it typically gave us lots of different ROIs. This is typically how the implementation works out. You can see we take the main picture and we divide the main picture into lots of regions of interest. We typically get thousands of ROIs for each and every picture. Now, obviously, if you end up doing this, there are lots of overlaps that you end up getting. So what we instead do is we instead go back and look at only a few ROIs. So we don't look at thousands of ROIs, but we only look at maybe a few hundred ROIs. And we can limit the number of ROIs based on what we call an object in a score. We can use something called an object in a score, and we can go back and limit the number of ROIs on the basis of what we call an object in a score. I repeat again, we can limit the number of ROIs on the basis of what we go back and call an object in a score. So this is how we can limit the number of ROIs, and we can say that so out of the thousands of ROIs that we originally had, we will only consider those ROIs where the object in a score was very, very high, or the probability of getting an object is considered to be very high. So that is how we go back and do the ROI identification part. So just to clarify again, so this is what we refer to as an RCNN based architecture, where we take the main picture and so after taking the main picture, we go back and so we take the main picture and we go back and we try to identify ROIs on the basis of the main picture. We try to identify ROIs on the basis of the main picture. So that is the first part of what we try to do. So in the selective search algorithm can typically find out lots and lots of ROIs, and we try to limit the ROIs based on what we call an object in a score. And that will only give us with a few hundred or a few, a few 50, 10, 50 ROIs here. And now we look at each and every ROI. We assume there is exactly one object inside it, and now we can perform object localization on the basis of that. So this is the selective search algorithm. And this is how we apply the RCNN based architecture. So we apply selective search, we identify the different ROIs in the image. Right now you can see there are total 1, 2, 3, 4, 5, 6, 7, 8. There are total 8 ROIs we are able to see. And then we take each and every regions of interest, which are sub pictures that we get. We take each and every regions of interest, and then we take out each and every region. And then on each and every region, we apply a CNN. Okay, I repeat again, we take apply selective search, we find out the regions of interest ROIs, and then we take out each and every region. And then for each and every region, we pass it through CNN, and then we go back and do the localization. So this is how we go back and do the whole thing. Then we take the second region of interest, and then we once again try to figure out that, hey, what is the object and where is the object? Then we take one more ROI, and we say, hey, what is the object and where is the object? So we take each and every regions of interest or each and every sub image, and we try to figure out where is the object and what is the object. So this is the way how we are driving this whole exercise. I hope all of you are able to get the sense of how the RCNN or the region-based CNN family of architectures basically work in practice. Okay, so one problem that we typically faced, one challenge that we typically faced here was, I would say, mostly with respect to, let's say, yeah. So once again, this is one challenge that we can say we faced here. So one of the challenges that we faced here was mostly with respect to the selective search algorithm. And if you see the selective search algorithm, primarily So one challenge that we faced with respect to selective search was it was fine. So we took that image, we divided that picture into multiple regions of interest, ROIs, 2000 ROIs that we got. And then for each and every ROI, we did localization. We tried to figure out where is the object in the picture and what is the object in the picture. That's how we learned the whole thing until now. That is the RCNN based architecture that we talked about. But what is the problem with this? The main problem with this is that you are actually ending up doing the CNN multiple times. This was a very simple architecture. It's very simple process we looked at. But the main issue that we faced here was we ended up doing the CNN multiple times. So the computation was very high. Okay. So good detection results, workable approach, but very slow, extremely slow. And the most important reason is because we're doing lots of CNN computations per picture. We're doing lots of CNN computations per picture. So doing almost 2000 odd CNN computations per picture. So that's the problem that we're actually facing. We're doing lots of computations per picture, and that is the main issue that we are actually kind of facing. Right, we're doing lots of computations per picture, and almost 2000 odd CNN computations per picture we are doing. So this is the RCNN based approach once again, and as I told you, for each and every ROI you're applying CNN only once. So if you're having 2000 ROIs, you're basically having 2000 CNNs. You're basically applying the CNN 2000 times. That's the problem. Okay, if you're basically having overall 2000 ROIs, then you're basically running the CNN 2000 times. That's what you're primarily trying to do. Overall 2000 times you're trying to run the CNN. So it's very, very computationally expensive. So if you're running the CNN model 2000 times, it's extremely computationally expensive. So how can we cut down on that? So how can we cut down on that? How can we go back and instead run the CNN only once? So enter something called fast RCNN. So where we are saying that, okay, we will not run the CNN 2000 times. Instead of running the CNN overall 2000 times, can we instead run the CNN model only a few times and work on the basis of that? So how do we make that work? So that is the whole idea. So we look at something called fast RCNN. So what is the basic idea behind fast RCNN? So fast RCNN does something like this. We are passing the image to the CNN right at the very beginning. We don't take the CNN at the end. You can see that architecturally the only change that we make is the CNN part we basically put here. So we take that picture, we pass that picture through the CNN right at the outset, right at the very beginning. We featureize that picture, and then we apply selective search on the featureized picture. Okay. Then whatever selective search that you're applying, we're applying that particular selective search on the featureized picture. So that's how we are running this entire. Okay, I repeat, we are running selective search primarily on the featureized picture. Okay, so that way we are taking that main picture, we are passing that main picture through the CNN only once. So we are taking that main picture, we are passing that main picture through CNN only once. So I repeat again, we're taking that main picture, we are passing that main picture through CNN only once, and then we are going ahead and we are basically applying selective search on the featureized picture. So whatever featureized picture we have got, now we are trying to identify that, hey, what are the regions of interest in that featureized picture. So that way the number of computations have also drastically come down. So we are only applying CNN only once. But ultimately, this is still working fine, because now whatever ROI identification we are doing, now we are doing that entire ROI identification on the featureized picture. That is the only difference, right? Overall, it's a lot faster, and obviously conceptually it's a lot more, it's a lot faster. But still there is a problem, because we are using the selective search algorithm. Selective search is kind of a non-deep learning based algorithm. It's a very basic rule based kind of an algorithm. So what was the next approach that we used? The next and the final approach that we used here was with respect to what we call faster RCNN, because fast RCNN still uses selective search. It was still very, very slow, as we saw, but it is very slow for real-time detection. If you look at real-time object detection, anything where you work with webcams and video sequences, frames per second kind of stuff, you need to be fast in terms of what kind of results you're expecting. And typically in these kind of use cases, you want to get very, very quick results. And in that particular context, it still used selective search. If you see, it was still using selective search primarily. So then enter faster RCNN. We started off with RCNN, then fast RCNN, then faster RCNN. In faster RCNN, everything else remains the same. This is what we had before. The only thing we do is we replace selective search with a deep learning algorithm. Instead of doing this, we actually introduced something called a neural network, and using a neural network, we identify the ROIs. Otherwise, the rest of the journey is very, very similar. Even in faster RCNN, the rest of the journey is very, very similar. The only difference is instead of using kind of a selective search to identify the regions of interest, we instead identify the ROIs using something called a region proposal network, which is much more accurate. So now we are able to use a proper neural network for identifying the ROIs. Okay, I repeat again, we're able to use a proper neural network to identify the regions of interest. That's the whole idea behind what we are doing as part of faster RCNN. I hope all of you are able to relate to this one. Everybody, I hope all of you are able to relate to this one. So we started off with something called RCNN, and as I told you, it's kind of like a divide and conquer principle where we are trying to solve a very difficult problem. And a difficult problem is a collection of many simple problems. So we are using selective search iteration 1. Take the main picture, divide the picture into multiple subparts with the assumption that every single picture has only exactly one subpart inside it. That is the basic assumption that we are making. So the whole assumption is that every single picture has exactly one subpart inside it. That's the whole assumption that we are making overall. Has exactly one object inside it, and then for each and every ROI, we are performing an object localization. That's how we are going about the whole thing. Okay, we are looking at each and every. So we are looking at each and every individual picture, and we are dividing each and every individual picture into multiple subparts. And this is with the basic assumption that each and every individual subpart there is exactly one object inside it. And now we are performing localization for each and every individual object. So that's how we are running the whole thing. That is selective search. Now, what is the main problem with selective search? The main issue with selective search was that it was a very slow technique. Selective search was technically a very slow technique. That's one challenge that we actually faced with respect to selective search. It was a pretty slow approach that we had, and obviously, so one of the things that we did was we tried to speed up. And the other main issue with RCNN, the initial RCNN based architecture, the main challenge that we faced with respect to RCNN, what was the main issue that we faced? So the main issue that we faced with respect to RCNN was that the RCNN based architecture was extremely slow, because we were actually doing the CNN part multiple times. We were doing the convolution part multiple times. So we were taking every single ROI and we were running it through the CNN multiple times. So that is why the CNN computation, one CNN computation itself takes so much time. And imagine that you're passing every single picture through the CNN. So you're basically doing 2000 localizations. You're having like 2000 pictures, and you're basically doing 2000 localizations for each and every observation. So that is extremely computationally expensive. It was not scalable. So that is when we started getting into fast RCNN. And fast RCNN, what we did was we first passed that picture through the CNN only once. We extracted the features of the picture, we featureized that picture, and then we passed it to selective search. In that particular featureized picture, we started to kind of figure out, we tried to figure out that, hey, like what are the regions of interest we are getting, and then for each and every regions of interest, we are trying to figure out where is the object and what is the object. So that's what we try to do. But finally, we looked at something called faster RCNN. That's even faster compared to this one. And there, what we did was we removed selective search and we introduced a region proposal network, which is going to do the ROI identification for us. So this is pretty much where we are right now. But the problem is that it is still very slow. It is still very slow comparatively. If you look at faster RCNN comparatively still pretty slow. It uses a deep learning model for ROI identification, which is very accurate, and it is still one of the most accurate object detection architectures out there, but comparatively still very slow. It still is 5 FPS, 5 frames per second. It's not really real time. Anything upwards of 20 FPS is what we can consider practically real time, but it is not really suitable for real time yet. So this is the part where we enter into SSDs. SSDs stand for single shot detectors, and YOLO. YOLO is a kind of an SSD model also. So this is the part where we enter into something called single shot detectors, SSDs. And this is the part where we try to expedite detection, because until here is fine. We understand the basics, we understand localization, we understand how to do localization on multiple objects. So we understand the divide and conquer concepts. We looked at three architectures: RCNN, fast RCNN, faster RCNN. But this was not working real time. Enter SSDs. In SSDs, let's see what architecturally what we are changing. So these are the three broad types of networks that we have talked about so far. All of you can look at the screen. We have a feature network. Feature network is what the CNN model is doing. It is taking the picture and it is basically extracting the features of the picture. This is what the CNN model is basically doing. Okay. Okay, this is what the CNN model is basically doing. The CNN part is basically taking the picture and extracting the features of the picture. And then we have the region proposal network, which is actually doing the ROI identification. And finally, the detector network is the object localization part. So we can basically bucket the entire architecture into three portions. One is the featureization part. Next is the region proposal part, and next is the detection part. This is how we are actually looking at the whole thing. But very clearly, what we are trying to do in SSDs and YOLO kind of architecture is we are basically cutting down on this part. So all the other architectures, we saw that in SSDs and YOLOs, we are only doing this part. We are cutting down on the middle region proposal part. Region proposal part we are not doing. There is no ROI identification that we are doing, actually. We're simply taking the picture, we are passing that picture through the CNN, we are featureizing that picture, and we are just passing that through the thing. So that is what we are doing. So there's no real region. So this is how we are actually working out right now. So we're taking the picture, we're passing it through a region proposal, and we're working primarily on the basis of that overall. Let us quickly see an architecture. These are the two popular SSD kind of architectures that we have. When we talk about single shot detectors, these are very popular SSD architectures that we have. We have something called multi-box SSD, and we also have something called YOLO. So these are two very popular SSD architectures that we have. So we'll quickly take a look at what SSD is. SSD is very, very fast comparatively, and we see what the architecture looks like. So faster RCNN was what we looked at. It was 5 FPS, where SSD clocks in at something around 60 FPS, which is extremely fast. But mind you, the speed is always compromised to some extent by the, so the speed definitely is compromised to some extent, by the overall accuracy. So if you want to build a very, a quick, a very fast model, then definitely the accuracy part will be compromised to some extent. So very fast model, the accuracy part will be compromised certainly to some extent. That's one way to look at the whole thing. So the speed will definitely, be compromised by the accuracy. So that's one way to look at the whole thing. So this is effectively the whole idea behind an SSD. So this is what we have talked about with respect to faster RCNN. We have the region proposal network, which is able to recommend the ROIs to you. And then we have the, this part. SSDs, what we do is we completely drop that ROI part, and we only have this. That's it. We take that picture, we pass it through CNN, we kind of featureize that picture. We pass it through CNN, we featureize that picture, and then what we do is we go back and identify. And we go back and identify the, what are the different class probabilities and the bounding box coordinates with respect to that picture. So that's how we are trying to do this. Again, we take that image, we pass it through CNN, we find out the features of the image, and then we are passing it through the detection layers, and that is the part that the localization part is actually working on. Now, the interesting part is who will provide the ROIs? Now, one question that people in this audience might have is that, Sayan, all this is good. You're saying that in SSDs, we are not doing any ROI identification. Then who will provide the ROIs in this case? Who will basically go back and provide the ROIs here? If there is no way to, so who will provide the ROIs in this particular case? So who will provide the ROIs here? That is one intuition that we have. So who will provide the ROIs? So we will have to provide the ROIs. And there is no algorithm, there is no approach that we are using to. So here we will provide the ROIs. So we have to provide the ROI coordinates. We'll tell the machine which regions to basically look for. So there's certain algorithms, there's certain guidelines that we will have, using which we will go back and tell that, okay, these are the specific ROIs where you should basically look for. Okay. So how do we go back and build ROIs in SSD? Let's quickly take an example. There are other there are other variants of SSDs that we have, and we'll go for another 15, 20 minutes here, guys. I know we're a little out of time here, but just another 15, 20 minutes we will do. We'll look at SSD, the architecture of SSD, and then we'll look at one small demonstration, and then we'll wrap it up. Okay, that's how we kind of pace it out. Yeah. Okay, so let us quickly see how the process of ROI rectification is done in SSDs. So what we basically did was we basically identified what we call priors, because as I told you, until now, until in all the architectures that we looked at, including RCNN, fast RCNN, faster RCNN, we had some networks that are doing it for us, and specifically in faster RCNN, we had something called a region proposal network, which was doing the ROI identification. Because only once we have the ROIs can we go back and do localization on that. So otherwise, we cannot do localization without the ROIs. So now let us see how this particular thing was done. How did we do the ROI identification kind of here? Let's try to see that part. Okay. So what we do is we divide that picture into multiple grids. So this was the approach that we defined. This is more of a rule-based approach that we basically had. So we took that picture and we divided that picture into multiple grids. Let's say we divide that picture into a 4x4 grid. There are total 16 cells that we have in this entire grid. And what we do is we look at the middle of each and every center point of each and every grid cell. And we treat the center point of each and every grid cell as an anchor box, as basically an anchor point. So these are basically called anchor boxes. It's another name for priors is basically anchor boxes. So what are anchor boxes? Anchor boxes are also called priors actually. Another name for anchor boxes are also called priors. So just to clarify, this is one more name for sorry, excuse me, anchor boxes. Anchor boxes are also referred to as priors. So we go back and look at each and every, we go back and create 4x4 16 anchor boxes, and the center point of each and every anchor box or each and every prior is basically what we call an anchor point. So there are 16 anchor points we're getting, which looks somewhat like this. Okay, and what we try to do is we try to go back and with each. So these are the grid cells we have created. Once again, just to clarify, this is the 4x4 grid we have got. So we have basically got total 16 grid cells right now. Just to clarify, we have got total 16 grid cells. So 4x4 grid, we have got total 16 grid cells. And then what we do is we consider each and every grid cell. We look at the center point of each and every grid cell. So we look at the center point of each and every grid cell. And that is what we call the anchor point. And then we use that particular anchor point as the baseline. So we take that particular anchor point as the baseline. So I repeat, we take that particular anchor point as the middle, and taking that to each of those 16 anchor points as the middle, we go back and draw anchor boxes of different aspect ratios. So we draw different anchor boxes of different aspect ratios. For example, if we take this particular anchor point as the center, so what we do is we draw different anchor boxes or priors of different aspect ratios. See, this is the anchor point that we have taken here. And then we draw different anchor boxes with different dimensions. Dimension 1, dimension 2, dimension 3. And each of these are basically called ROIs or priors or anchor boxes. These are the different terms that we can use. So as you can very clearly see, unlike the other approaches that we have studied, here the ROI identification is done totally by rules that we have defined. This is the approach that we are defining. So create a 4x4 grid, identify 16 grid cells, 16 anchor points, center around each and every anchor point, and draw different anchor boxes of certain dimensions of different aspect ratios. And so right now we are basically getting total 6 anchor boxes or 6 ROIs or 6 priors that we have defined. And we'll make an assumption that there is each and every, within each anchor box, there is each and every, there's one object present. And for each and every that, we'll go back into object localization. That's how we'll actually write the whole thing. And this is how we'll do it. So we can see how many ROIs we will have for this. This is 6. And since there are total 16 anchor points, we'll have total 96 priors. And this is how we can define the math around it. Okay. So this is how we'll do this. Okay. Will any of the 96 ROIs overlap? Yes, it might. So we might have a scenario where there's overlapping happening, and we'll discuss in a minute from now how to handle that overlapping. Okay. How to build ROIs which will overlap well with bigger size objects in the image. Right now, what we saw were very smaller size things, right? So these anchor boxes ROIs will only capture very small details in the object, right? But how do we capture bigger details? So what we can go back and do is we can kind of take so to capture bigger details, we can kind of take bigger grids. Let's say we can take a 2x2 grid, and if I take a 2x2 grid, we basically have total 4 grid cells. Okay, I repeat, if you have a 2x2 grid, we overall have total 4 grid cells, and then we can look at the center point of each and every grid cell, and we can say, and we can draw priors around it. So this is the center point. We have taken anchor points. We have taken 4 anchor points. Yes, anchor points are basically always the center of the grid. They're always the center of the grid actually. So now we go back and consider the center point of each and every grid cell, and around that we go back and draw the different anchor boxes or the priors. So right now we've got total 4 anchor boxes here. We've got total 4 anchor boxes here. We can also have a 1x1 grid, and a 1x1 grid will capture more detail. If I look at a 1x1 grid, you can see typical 1x1 grid will capture more detail. We can once again consider one grid cell. We can consider the center point, that anchor point. Around that anchor point, we are drawing multiple anchor boxes. So we are having multiple anchor boxes, which looks about like this to cover really big objects. Okay, so this is how we are actually driving the whole exercise. Okay, so the number of ROIs in the SSD are determined completely by us. It is something that completely we are predefining. So we are defining the number of ROIs in SSD, something that, as I told you, something that we are completely defining. It is completely decided by us based on the dimensions of the grid, how many grids we are having, how many grid cells we are having, how many anchor points we are having, and what type of anchor boxes we are having. It is completely determined by us. Okay, so as I told you, the number of ROIs in the SSD are completely determined by the number of grid cells, the number of anchor boxes you have, the number of anchor points you have, and as I told you, it is completely determined in a way by us. Number of grid sizes, number of priors in each grid cell, it is totally determined by us. All these are something that we decide. Okay, and this is typically the whole idea. Just to summarize once again, so we identify certain grid size, something that we predefine. Different SSD architectures or even different YOLO architectures, they have their own standards. And this is the theory part. You can look at the documentation where we get into this in a bit more detail as to what kind of standards we follow typically. So we have got different standards for different types of architectures. This is a general standard I'm talking about, where if you identify a 2x2 grid, there are total 4 grid cells, and you will identify the center point of each and every grid cell, the anchor points. And with respect to the anchor points, you will form, let's say, in this case, 3 plus 4 ROIs. So 4 ROIs per anchor cell. So 4 ROIs per anchor cell. And now we can say that, hey, there are total 16 ROIs we will get. Okay, so 1x1 grid, we have got total 1, 2, 3, 4, 5, 6 ROIs right now, as you can see, for this particular 1x1 grid. So that's how we have done this entire thing. For the 1x1 grid, we've got total 4 ROIs we've got here overall. And for really small objects, let's say if you have some really small objects in the image, give an example. If you have some really small objects in the image, then we will basically go back and look at a 16x16. So 16x16 grid is used if you have, let's say, some really small objects in the image. If you have very, very small objects in the whole image, we use a 16x. So that's the encryption overall. Okay. Okay, so how many ROIs? Let's look at this. This is from the SSD paper, the original SSD paper that is published. This is from the original SSD paper. So we take a 38x38 grid, and we assume that there are 4 priors per cell. So 38. So what is the number? How does the number work out? Let's take a look at this one. So for example, if you have a 3x3 grid, there are total 9 cells we have, right? Imagine this is a 3x3 grid. So there are total 9 grid cells. There are total 9 anchor points, and for each and every anchor point, there are 4 priors. 4 anchor boxes or ROIs that we are drawing around each around each anchor point. So 9 4 are 36. That's how this particular number is coming. Okay. So there are 9 grid cells. That means there are total 9 anchor points, and around each anchor point we are drawing 4 ROIs. So we are having total 36 ROIs or 36 priors or anchor boxes. These are the different terms that we can go back and use. So total we will end up having 8,732 ROIs. So how many ROIs are we having? Theoretically, how many ROIs are we defining? We're defining total 8,732 ROIs. All of you can see this one. And now we can go back and say how many outputs are we getting? We're getting that many number of outputs. Because mind you, that for each and every ROI that we identify, we will go back and do object localization. So that's a two-step process. First step is you take the main picture, you identify how many ROIs in that picture. There are 8,732 ROIs, that is 8,732 sub pictures we are getting. And then for each and every ROI or each and every sub picture, we go back and do object localization. So we are basically doing 8,732 object localizations. So that many number of outputs we are trying to predict, and that many number of bounding boxes we are trying to predict. So that's what we are probably all of you are able to see this one, right? So that many number of outputs we are trying to predict, and that many number of kind of bounding boxes we are also trying to predict here. We're trying to predict that many number of outputs and also that many number of the bounding boxes. But one thing that will actually happen, here practically, if you think about it, is we will end up getting lots of overlaps, right? If you look at the model prediction, the model prediction also what will happen. All this what we are discussing is part of model training. You take the picture and you identify 8,732 ROIs and you try to go back and do 8,732 object localizations you're doing. But all of this is part of the model training. Model prediction, same thing will happen. Model prediction also the idea is the same. You identify 8,732 bounding boxes, and for each and every ROI you try to do a prediction. So imagine you are getting 8,732 boxes. That is very difficult. Imagine you are doing object detection and you take a picture and the model returns 8,732 boxes. That is very difficult. So how many objects will be predicted by the model? As many as number of ROIs. So if there are 8,732 that you're getting for SSD is just another YOLO kind of architecture. YOLO is very similar actually. So we will end up having 8,732 predictions. That is not what we want, right? There are a lot of overlaps we will get, a lot of backgrounds we will get. So what we try to do in the prediction stages, images will typically have only a few objects, not thousands of them. So what the architecture tells us right now is, theoretically we are saying that, okay, we take the picture and we divide that picture into 8,732 ROIs, where we supposedly think there are objects. But in reality, there won't be 8,732 objects in the whole picture. Definitely there won't be, right? So how do we cut it down? So what we do is in the model prediction stage, imagine now we have the trained model. The model prediction will happen, right? Let's say for each and every picture you feed in, the network will once again go back and identify 8,732 ROIs. This is the static way we will identify 8,732 ROIs in the picture. And then for each of those 8,732 ROIs, we will go back into the localization. We'll identify where that object is and what is that object. So effectively, we'll end up building 8,732 bounding boxes. This is the prediction that will happen. Now, out of that, we will remove all the background predictions. There will be thousands of background classes we will end up having. So out of 8,732 bounding boxes we will end up generating, most of them will be background, we'll remove that. Now, after that, what we'll do is we'll be left with a much smaller number of predictions, say 100. Out of that, we go back and remove the duplicate overlapping predictions. And we use a specific technique called non-maximum suppression. And what is that idea? Let's see that. You might end up with something like this. Let's say you have a bounding box here which predicts a dog with 93% probability, another bounding box of dog with 91% probability, another bounding box of dog with 87% probability. You might end up with something like this. Okay, we end up seeing a dog with 93% probability, we end up seeing a dog with 91% probability, and we end up seeing a dog with 87% probability. This is not what we want, right? We only want a single dog object. Output will look very congested, very clumsy if I end up with an output like this, right? But this is exactly what will happen. So I don't want all the three outputs. What I will do is, if I end up seeing this kind of overlapping bounding boxes, what I will do is I will only consider that particular bounding box which has the highest probability. I will ignore the other two. I will only take the one where the dog is 93% probability. Similarly, for the cat, you might get a bounding box with 97% probability, bounding box with 96% probability, and bounding box with so we will only go back and consider, we use non-maximum suppression technique, and we'll only consider that particular bounding box with the highest confidence. We take the one with the highest confidence. In this case, we will consider only the 2 plus 2. This is how we will go back and use something called non-maximum suppression and only consider those bounding boxes with the highest probability of prediction. And that is how we get the final prediction. It will be down to hardly one or two different, a few bounding boxes we end up in. And that's the crux of what we are trying to do in the prediction phase of SSDs and YOLO kind of architectures. Where we are taking a picture, we are basically generating thousands of bounding boxes based on the architecture, how many ROIs you have defined manually. Then we are removing the background predictions. Then we are removing the duplicate predictions using non-maximum suppression. And finally, the final predictions are actually coming out. That is the crux of what we are trying to do. Okay, this is a small summary of what we have talked about until now. I hope this will beautifully summarize the idea behind object detection. And I will show you one final hands-on along the way to wrap up the session. This will be another 5 minutes of session time I'll give all of you. So this is the general summary. So we talked about localization, which was about single objects in the image. This was the most important part of the conversation we had, because it is important to understand how the architecture is getting built. Detection is just a follow-on from there. Okay, and object detection is more about having multiple objects, divide and conquer. So we break the picture into multiple sub-pictures and we perform localization on each and every sub-picture, because the assumption is that it is considering one object inside it. Okay, there are different approaches we talked about. So this all belongs to a family of models that we refer to as RCNN-based models, region-based CNN models. And you can see region-based CNN model, the initial one, it uses something called selective search. The whole idea is how you take that picture and how you divide that entire picture into ROIs or regions of interest. How you take that picture and how you divide that main picture into ROIs or regions of interest. And on each and every region of interest, you go back and perform object localization. Okay, on each and every picture, you perform object localization. You identify what is the object in the picture, and you identify where is the object in the picture. You do object localization on each and every sub-picture. So we looked at selective search, RCNN, fast RCNN, and faster RCNN used RPN. RPN was very, very slow actually. So, and it was also very accurate. Then we use SSD. SSDs and YOLO kind of architectures are very similar actually. YOLO belongs to a kind of single shot detector kind of architectures. So architecturally, they're very similar. The only difference primarily is with respect to the architecture in terms of the grid cells and the grid sizes and all that. Otherwise, they're very, very similar with respect to what we do. Okay, we look at a real-time object detector model right now. Let's see how to build an object detector. And this is the TensorFlow model detection zoo. We can all see this is the model detection zoo where we can see a list of all the pre-trained models that we have. And typically the architectures will go somewhat like this. For example, faster RCNN inception net. What is the meaning of this? Inception net is basically the CNN part of the architecture. That is the part that you're using for transfer learning. Okay, because we know in SSDs and region-based CNN models, one is the featureization part of the architecture, and the second is the detector part. So faster RCNN is basically the main backbone, the main object detection backbone that we're using. And inception net is basically that particular transfer learning based architecture that we're using just purely for the featureization part. Okay, SSD mobile net, what does it mean? What is the nomenclature? How do you read this? SSD is the backbone architecture, and mobile net is basically the featureization model. So which particular pre-trained model you're using for featureization purpose? That's how we use it. Right? So we'll run this one. We'll quickly run this one. I'll just go back and use GPUs along the way and just download this and run this one quickly. And we'll load this model. And what I will try to do is I'll try to take in a couple of these, kind of sample examples and try to show you how object detection is working. We'll take a couple of images from the TensorFlow website and we'll try to see how object detection is working. This is how it will basically look like. When I take a picture of these two dogs, the model will identify, it will basically identify where the dogs are and what is the classes of the objects. It is still loading the model here right now. It is taking it from the repository. These are all pre-trained models we are looking at. We already saw how to build a model. It's the mostly pre-trained models we are seeing right now. And you can see an example here, as I was telling you, the example of the dog. You're seeing a picture of the dog, and we're able to see what classes that particular picture corresponds to. And the second one we're able to see is with respect to the other scenery. We're able to see a particular, scenery of a beach, and we're able to identify what are the pictures and what are the classes of the pictures. We're able to see that. It will also give you the class probabilities, and it's very accurate actually. You can see the kite is 58% probability, the person is 100% probability, the person is 96% probability. It's pretty accurate, the architecture. And we can do this for a range of other examples. The group photo, you can again see the bounding boxes are very accurately coming for the group photo. Aeroplanes parked on the way, and the model is able to identify very accurately, where the plane is and what it's able to identify. Okay. This is the crux of what we are trying to do in object detection. All of it, I think, pretty much, and then you can actually see from these real world examples also that the theoretically what we talked about, all these architectures will give us, let's say, thousands of ROIs initially, but it's very difficult. Imagine that this picture we are outputting thousands of bounding boxes. It will be so difficult to read this one. So we will not do that in practice. So in practice, what we'll do is we only look at a few 10, 50 or 100 ROIs and work on the basis of that.